Almost everything we had drawn of the edge of the solar system turned out to be wrong, and we only know that because of Voyager. Two small spacecraft went out there expecting a clean line and found a restless, contradictory place that broke nearly every prediction we had made for it. Voyager 1 is 14 billion miles away now, still moving, and for 46 years it has been sending word home. Then, one night, the word stopped meaning anything. So tonight we follow it out to that edge. What did Voyager find? Light is the fastest thing the universe allows. Nothing carries information more quickly. A command leaving a dish on Earth, moving at that absolute speed, still takes close to 22.5 hours to reach Voyager 1. If Voyager replies, the answer needs another 22.5 hours to come home. 45 hours for one round of speaking and listening. A question asked at breakfast cannot be answered, at the very earliest, until the following evening. The travel time itself is a ruler. Light covers about 670 million miles every hour, so 22.5 hours of one-way lag places Voyager more than 14 billion miles away, and you can read that distance straight off the clock with no other instrument involved. Every additional second the signal takes is a few 100,000 more miles of separation, surveyed by nothing more sophisticated than waiting. Voyager moves outward at close to 1 million miles a day. In the 22.5 hours a single message spends crossing the dark toward us, the spacecraft travels almost 800,000 miles past the spot where it stood when it spoke. More than 3 round trips to the moon, opening up between Voyager and its own sent words, while those words are still in transit. We never hear from where Voyager is. We hear from where it used to be. The position fixed inside any message has already become a memory by the moment it arrives. We know, to the mile, where Voyager was. Where it sits at this exact instant is a thing no signal will ever be fast enough to tell us. And the thread carrying even that aged news is impossibly thin. Voyager sends data home today at roughly 160 bits per second. At that rate, dragging a single ordinary phone photograph across the gap would take most of a day by itself, and a short video clip would take years to arrive in full. Everything we have ever learned from the edge of the solar system has come seeping through a channel slower than the earliest home modems, broadcast by a transmitter putting out about the power of the little bulb inside a refrigerator door. The machine on the far end of that thread was built to the limits of the 1970s. Each Voyager computer carries something near 70 kilobytes of memory in total, less storage than a single photo on a modern phone, and executes a few tens of thousands of instructions a second, while the handset you might be holding runs hundreds of thousands of times faster. On a system that lean, every block of memory is precious, and there is almost nowhere to absorb a mistake. That fragility surfaced a little over a year before the long silence. Voyager began returning scrambled reports about its own orientation, readings that made it look as though it had lost all sense of which way it was facing. The spacecraft was entirely healthy. Its antenna was still locked onto Earth exactly as planned. What had failed was its ability to describe itself to itself, because the system meant to report its orientation had started quietly routing that information through a worn-out stretch of onboard computer. Then, in November of 2023, the deeper failure arrived. Voyager kept transmitting on schedule, never once missing its appointed slot. But the signal came down as a frozen, repeating string of ones and zeros, the same dead pattern looping endlessly. A single region of memory inside its flight data system, The part of the spacecraft that gathers and packages every reading before transmission had been corrupted, and that one ruined patch was garbling every word Voyager tried to assemble. A machine the size of a small car, more than 14 billion miles out, was still phoning home on time, with nothing left to say that anyone could read. Repairing it meant working blind across that wall of hours. On a desk, you alter one line of code, watch the result the same second, and adjust. Across 45 hours, you compose an instruction, release it into silence, and wait 2 full days to discover whether the spacecraft you pictured while writing it still matched the spacecraft that finally received it. Each attempt was a bet placed on a version of Voyager that had already drifted onward by the time the bet arrived. A single guess cost 2 days. A genuinely difficult problem could devour dozens of those guesses in sequence, which is how a software fault grew into a 5-month silence. The corruption sat on a chip that could not be patched where it lay. So the team decided to lift the damaged code out entirely and slot it into other corners of memory that still worked. And because no single empty block was large enough to hold it whole, they had to split the code into fragments, scatter them, and rewrite every internal pointer that referred to them. They sent the first piece in April of 2024 and waited the full 45 hours for any word back. 2 days later, across more than 14 billion miles, a signal returned that carried meaning again. A 47-year-old computer had been coaxed, fragment by scattered fragment, back into sense. No signal of any design crosses 14 billion miles faster than light, and light is already burning most of a day on the journey. The 45-hour delay is simply the universe applying its one unbendable speed limit to a conversation stretched across an ocean of vacuum. And the wait lengthens with every day that passes. Voyager lays down close to another 1,000,000 miles every 24 hours, and each message home takes a sliver longer than the message before it. The round-trip exchange is creeping toward being whole hours longer inside a single human lifetime, and the data limping back grows thinner each year as the power supply fades. We say it almost in passing that Voyager reached the edge of the solar system. Out there, at the far side of that day-long silence, what edge had it actually crossed? Where does the solar system end? We picture a clean outer rim, the way a coin has an edge, and imagine that somewhere past Neptune the sun's territory simply stops. Out there, the sun keeps no such border. What it keeps instead is a handful of influences that each fade at their own pace, and they fade so unevenly that the solar system ends in at least 3 entirely different places, separated by tens of thousands of times. The span between the Earth and the Sun, 93 million miles, is one astronomical unit, and everything farther out gets counted in those lengths. Neptune rides about 30 units away. The familiar map ends there, with Neptune as the last great planet, but Neptune is no border, only the farthest place where the young solar system managed to pile enough rubble together to build a world. Beyond it, the Kuiper Belt scatters its frozen debris out to around 50 units, Pluto among the larger pieces, and across the whole of it, the sun still shines and pulls and blows precisely as it does here, undiminished in any way that counts. The first real frontier the sun builds comes from its wind. Every second, it sheds more than 1,000,000 tons of itself as a thin gas of charged particles flung outward at close to 1,000,000 miles an hour in every direction at once. That wind inflates an enormous bubble, the heliosphere, around the sun and all its planets. The wind cannot stay strong forever, and the reason is pure geometry. As it streams outward, it has to fill ever larger shells of space, so its density drops with the square of the distance. By the place where Voyager crossed, the wind has thinned to more than 10,000 times weaker than it was near Earth, finally too feeble to hold back what lies beyond. And what lies beyond is not empty. The sun is currently drifting through a warm, wispy cloud of interstellar gas, a few thousand degrees and almost unimaginably sparse, that presses inward on the bubble from all sides. Where the failing wind and the inward press of that cloud fight to a standstill, near 120 astronomical units, about 11 billion miles out, the wind's territory ends. That standoff is the wall Voyager went through. The sun is not anchored in that cloud either. It travels through the local gas at around 50,000 miles an hour, which gives the whole bubble the lopsided form of anything in motion, a rounded nose pressed toward the direction of travel and a long tail drawn out behind. For decades, the diagrams showed a sharp shock wave standing off that nose, the kind of bow wave a boat shoulders ahead of itself through water. Closer measurements have since hinted that the sun slips through the cloud too gently for a true shock to form, so the leading edge is likely a softer swell, and the real shape of the tail is still argued over. It is the outermost wall of our own solar system, and we are not yet sure what it looks like. That wall is only the first of the endings. Gravity keeps no wall, because gravity never switches off. It merely thins by the square of the distance, the very same geometry that drained the wind, and it goes on gripping long after the wind has died away. The proof of that grip is the comets. Some of them come falling out of the far dark on orbits that take millions of years to close, which means the sun has been holding them, quietly, across reaches the wind never approached. A frozen world called Sedna swings out beyond 900 astronomical units at its farthest, more than 5 times deeper than Voyager has yet traveled, and the sun reels it home every time. Farther out still, a vast and faint shell of icy bodies is thought to wrap the entire system, the nursery of the long comets, and its outer edge marks the true gravitational limit, the radius where the sun's hold finally yields to the pull of neighboring stars and the slow tide of the turning galaxy. That limit sits near 100,000 astronomical units, a quarter to a half of the way to the next star over. Set against it, Voyager, for all its speed and all its decades, has crossed about 1 part in 600 of the way, and will need tens of thousands of years to finish the rest. There is a third ending, larger than both. The sun is a star, and from far enough off it would shrink to a single point of light among the rest. Carry it outward in the mind until human eyes could no longer find it in a dark sky, and that vanishing distance falls somewhere around 50 to 70 light years, more than 3 million astronomical units. Within about 10 light years, the sun would still hang there as a plainly visible star. Only out past 50 does it slip below the threshold of sight. By the measure of where the sun stops being visible at all, our solar system reaches far enough to enclose hundreds of neighboring stars and whatever worlds they carry. 3 endings, then. The wind near 120 units, gravity near 100,000, the light past 3 million. The same sun, asked 3 fair questions about where it stops, returns 3 answers that disagree by tens of thousands of times. And Voyager sits in the oddest place the arithmetic permits, past the first ending and nowhere near the other 2. At this very moment, the spacecraft is both outside the solar system and buried deep inside it, loosed from the sun's wind, yet firmly held by the sun's gravity and still washed in the sun's light. None of those contradict each other. They are 3 different truths about a single point in space. For a long time, I assumed all this disagreement meant we simply hadn't measured well enough, that a finer instrument would one day land on the real edge. The finer instruments only made it worse. They confirmed every answer at once. The edge of the solar system is less a fact waiting out there to be found than a choice we make about which piece of the sun we have agreed to follow, while the sun, indifferent, goes on ending in 3 places at the same time. Only one of those endings was something Voyager could feel in the instant it crossed, a place where the space around the spacecraft physically became something else. When the sun's wind finally reached its limit, out at that 120-unit mark, what happened to it there? Everyone expected the wind to die quietly. The reasoning behind that was sound. The solar wind thins as it travels, by the square of the distance, the same geometry that empties any spreading flow, so the natural picture was a wind growing slower and fainter mile after mile, until it simply blended into the gas between the stars, with no clear line dividing the two. A long, soft fade, the way a sound trails off in a large room. That is not what Voyager found. In late 2004, almost 94 astronomical units out, Voyager 1's instruments caught the wind doing something a gentle fade cannot do. Its speed collapsed, dropping from close to 1,000,000 miles an hour to a small fraction of that, across a transition far too sharp to call a fading. The wind had struck something, and rather than slowing the way a runner tires, it braked into a slower state all at once, piling up, heating, thickening into a thin front. A shock. The same kind of sudden wall of compressed gas that stands ahead of a supersonic jet. The reason the wind cannot fade gently is hidden in one strange fact about it. The solar wind moves faster than its own pressure waves can travel. In any gas, a disturbance ripples outward at the speed of sound for that gas, and that ripple is the only way one patch of gas can warn another that conditions have changed ahead. The solar wind outruns its own warnings. Near Earth, it is already moving perhaps 10 times faster than any signal could travel back through it, hopelessly supersonic by the standards of the thin gas it is made of. No message can fight its way upstream to tell this oncoming wind that an obstacle waits ahead. So the wind arrives at the interstellar gas with no preparation at all, at full speed, unable to slow down smoothly, because slowing smoothly would demand advance notice it can never receive. All that remains is to brake violently in a razor-thin shock, spending its speed as heat and compression in an instant. A wind that has outrun the news of its own ending can only end like that, in a wall. The wind carries more than particles into that wall. As it streams outward, it drags the sun's magnetic field along with it, and because the sun is slowly turning, that field gets wound into an enormous spiral, the way the water from a spinning sprinkler curves into long arcs. By the time it reaches the shock, that whole spiraled field is being crushed and folded together with the slowing gas. Beyond the shock, the character of everything shifts. The wind, now slowed and heated, spills into a wide and churning region where it no longer drives straight outward. It begins to turn, swept sideways and then backward, draining off down the long tail of the bubble like water curling around the stern of a moving ship. This turbulent zone runs on for tens of astronomical units, billions of miles of wind that has been stopped in its tracks and turned, still solar, still carrying the sun's tangled field, yet going nowhere outward any longer. Then, in August of 2012, near 121 astronomical units, Voyager 1 crossed the final seam. Over a span of only days, the particles streaming out from the sun fell to about 1,000th of what they had been, while the steady rain of high-energy particles from the wider galaxy climbed and held. For a boundary 11 billion miles across, it proved astonishingly thin, less a gradual shoreline than a clean cut between two worlds. On the near side lay the sun's plasma, On the far side, the plasma of interstellar space. And the two refuse to mix. The solar wind slides along the inside of that membrane, while the interstellar gas slides along the outside, each pressed to its own face of the seam, neither bleeding into the other. Two rivers meeting and running side by side along a single bank, refusing to become one water, because each carries its own magnetic field and its own pressure, and the seam holds exactly where those balance. What that crossing overturned was not a number but a picture. We had imagined the solar system ending the way a sound dies, growing quieter until no one could say where it stopped. It ends instead like a coastline, a definite line with one medium on each side, sharp enough that a spacecraft can pass through it in an afternoon. Underneath the violence of that shock, though, sits something quieter that has stayed with me. The wind reached the very limit of the sun's domain without ever being able to feel it approaching. It pushed outward for 11 billion miles, at 1,000,000 miles an hour, carrying no possible knowledge that an ending lay ahead, and arrived at that ending at full speed. Yet when Voyager 2 reached the same boundary, it met it in a different place, years apart from its twin. Was the edge of the solar system even holding still? A wall you can name and place ought to stay where you put it. When Voyager 2 at last reached the same heliopause its twin had crossed, it slipped through at almost the same distance, around 119 astronomical units against Voyager 1's 121. Reassuringly close. But the two crossings fell 6 full years apart, and the probes were nowhere near each other when they happened, one climbing up and out of the plane of the planets, the other angling steeply down below it. Two travelers, on two different roads, arriving at the same border 6 years and billions of miles apart. Part of that gap is plain bookkeeping. Voyager 1 moves faster, about 3.5 astronomical units a year, and had a head start toward the edge, while Voyager 2, slower and pointed in another direction, was always going to arrive later. Speed and aim do not cover all of it, though, because the boundary the second probe crossed was not sitting where it had been when the first one went through. The edge had moved. The heliopause holds its position exactly where two pressures cancel, the sun's wind pushing out and the interstellar gas pressing in. Neither of those holds still. The sun runs on a roughly 11-year cycle, climbing to a stormy peak thick with flares and outbursts, then sinking into a long quiet, over and over. When the sun is loud, its wind blows harder and the bubble swells outward. When the sun falls quiet, the wind slackens and the bubble draws back in. The whole boundary, 11 billion miles away, rises and settles in time with that slow pulse, shifting its position by several astronomical units across each cycle. The engine underneath the pulse is the sun's magnetic temper. About every 11 years, its magnetic field tangles itself, peaks, and flips, and the surface erupts more violently, flinging out enormous clouds of charged gas. Each eruption is a pressure pulse launched into the wind, and when several travel outward together, they can shove the boundary further still, a hard gust laid on top of the long breath. There is a quiet delay folded into all of this. A change in the wind never reaches the boundary at once. It has to ride all the way out at the wind's own speed, and that crossing takes well over a year. So the edge of the solar system is never answering to the sun as it is now. It is playing out the sun's mood from more than a year in the past, a storm long since faded back home still arriving, late, at the wall. The breathing does not even happen evenly. The surface never swells as one clean sphere. It bulges and sags from place to place, ripples traveling across it, some patches pushing outward while others fall back. And when researchers studied how far the boundary had shifted between the two crossings, the changes came faster and less regularly than any model of the heliosphere could reproduce. The wall moves in ways the equations have not caught up to, and that piece of it stays honestly unexplained. The distance to the edge was never uniform in every direction to begin with. The nose of the bubble, pressed forward into the sun's path through the galaxy, rides closer in than the flanks, while the tail streams far behind. Both probes left through that forward hemisphere, but one high above the plane of the planets and one well below it, so even a perfectly motionless heliopause would have been met at different distances along their two routes. A breathing one made the difference certain. Set all of it side by side and the boundary stops being a place at all. Even after you have chosen the wind as your definition and settled on the heliopause as your line, that line is still breathing, drifting in and out by several astronomical units while ripples cross its surface and year-old solar weather plays out along it. And the inward pressure shifts across the ages too. Since the cloud the sun is crossing has its own thick and thin regions, so, over thousands of years, the baseline size of the whole bubble grows and shrinks as the sun drifts through denser and emptier interstellar gas. An honest map would draw the edge not as a circle but as a slow tide line, a band a few astronomical units wide whose exact position depends on the year you ask. What stays with me here is the rhythm of the thing. Something the size of the solar system, breathing. A single breath of that bubble takes 11 years to finish, drawing out and easing back on a cycle longer than a childhood, and it has been doing this, without pause, for the whole life of the sun. The edge of everything the sun touches rises and falls like a chest in deep sleep, on a breath so long that no person will ever feel a single one of them complete. The two probes never truly measured that boundary. They touched it twice, 6 years apart, and caught it at two different moments of a breath that never stops. Everything we know of the shape and motion of the edge comes from those two fleeting contacts, two fingertips brushing an enormous moving surface at two separate instants, and from them we are trying to read the whole long rhythm. That may be the strangest part of the achievement, and it turns the attention back toward the people who made it possible. A boundary that breathes on an 11-year pulse, 11 billion miles out, was reached by machines drawn up and launched before anyone alive knew for certain the boundary was even there. Their builders aimed at a target they could not see, one that would never stop moving, one that most of them would not live long enough to watch their machines arrive at. What does it take to build something like that? The whole mission existed because of a coincidence in the sky that comes around about once every 176 years. In the mid-1960s, a young engineer named Gary Flandreau, mapping out future spacecraft paths, noticed that the outer planets were drifting toward a rare arrangement. Jupiter, Saturn, Uranus, and Neptune were all swinging toward the same broad stretch of their orbits, close enough together in the late 1970s that a single spacecraft, aimed precisely, could fall past one, borrow its gravity to fling itself onward to the next, and repeat the trick all the way to the edge. The last time the planets lined up this way, Thomas Jefferson was being sworn in as president. Missed the window, and it would not come again until the 22nd century. The maneuver that made it work is a kind of theft so gentle no one is robbed. A spacecraft swinging close behind a moving planet gets pulled along by its gravity and carries off a tiny share of the planet's orbital motion, leaving faster than it arrived, while the planet loses a sliver of speed too small to ever detect. Voyager came away from Jupiter tens of thousands of miles an hour faster than it went in, enough to break free of the sun entirely, then took another push from Saturn. Each planet handed the probe to the next like runners in a relay, and a craft that could never have carried the fuel to reach the outer planets on its own arrived on borrowed motion. But the planets had to be in exactly the right places, and the path had to be calculated years in advance by people who would then wait more than a decade simply to learn whether the final handoff had worked. The machines built to ride that path had to survive conditions no one could fully test for on the ground. Everything that mattered was doubled, 2 of each computer, 2 of each system, so a failure in one could be answered by its twin. The electronics were kept deliberately plain, with no fragile cleverness waiting to break, and the most delicate parts were armored against radiation because the route ran straight through the most savage radiation belts in the solar system, around Jupiter, where a single pass delivers a dose roughly 1,000 times what would kill a person. Voyager flew through that and came out still working. And to keep running for decades in a place where sunlight is far too feeble to power anything, each probe carries its own small nuclear heart, a slug of plutonium whose steady radioactive warmth is converted into electricity. No panel of solar cells could have managed it out here. The sun, from this far, is only another bright star in the dark. All of this was assembled for a mission meant to last about 4 years, just long enough to study Jupiter and Saturn and be done. It has now been running for 47. The people who designed it built far past what the job in front of them demanded, and by doing so, they handed a working spacecraft to a future they could only guess at. Keeping it alive has demanded something they could never have built into the hardware. The probes speak an old computer language that very few people are still trained to read, their instructions written in a style already aging when the machines left Earth. The manuals survive on paper and microfilm. The team that flies them has shrunk over the years to a group small enough to fit around a few tables. Across nearly 5 decades, the knowledge of how to talk to Voyager has had to be carried from one set of engineers to the next, taught and retaught. And when the hardest faults appeared, people who had retired years before were called back in to read code they had written as young men and women, because they were among the last who still could. The hardware can be built to endure for 10,000 years. The understanding of how to use it cannot be welded on. It lives only in people, and it has to be handed along, voice to voice, or it dies out even while the machine keeps going. Voyager will almost certainly outlast the last human being who knows, by heart, how to speak to it. Everything it still tells us tonight rests on a thin and thinning line of people who chose to learn an obsolete language in order to hold a conversation with something that left before most of them were born. The engineers of the 1970s were, in effect, writing a letter meant to be opened by strangers decades later, knowing they would not be in the room to explain a single line of it. They could not meet the people who would inherit the work. They could only build carefully enough and write plainly enough that those strangers might have a chance of carrying it forward. And carry it forward they have well enough that when the instruments out at the edge began sending back a reading that made no sense, no one's first instinct was that the spacecraft had failed. The machine was sound. The measurement was simply impossible. Space, it insisted, was growing denser the farther out Voyager went. How could emptier ever come to mean thicker? Everything in the first part of the journey trained the same expectation. The solar wind thins as it travels, by the square of the distance, so the farther Voyager went, the emptier its surroundings grew, mile after mile, exactly as any spreading thing should grow thinner. By the time it neared the edge, the wind around it had fallen to a few thousandths of a particle in each cubic centimeter, an emptiness that makes our finest laboratory vacuums look crowded. The guess was that crossing into open interstellar space would simply continue the trend. Emptier still, then emptier again. The opposite happened. In the last stretch of solar wind, just inside the wall, the gas had thinned to roughly 2/1000ths of a particle per cubic centimeter. Within days of crossing the heliopause, the density around Voyager 2 leapt to about 4/100ths, some 20 times higher, close to what the models had predicted for interstellar space. Then, rather than settling at that value, the number kept climbing as the probe pressed deeper, past 1/10 of a particle per cubic centimeter, growing thicker the farther out it traveled. Voyager had spent decades watching its surroundings thin toward nothing, and then, beyond the wall, space began filling back up. This was not one probe's fluke. Voyager 1, which had crossed 6 years earlier in a different direction and read its surroundings by an indirect method after its own plasma sensor died back in the 1980s, had already seen the very same thing, a density that rose and went on rising with distance. 2 instruments, 2 paths, 1 impossible trend. The resolution is that Voyager had passed from one kind of space into another, and the two run on completely different rules. Inside the bubble, the density of the gas is set by the sun. It is solar wind pouring out from a single source, so naturally it thins with distance, the way the spray from a hose spreads and weakens the farther it flies. Outside the bubble, the sun has nothing to do with it. That gas belongs to the galaxy, the thin interstellar medium filling the spaces between all the stars, and its density depends on where you stand in the galaxy, not on how far you happen to be from any single star. The warm local cloud the sun is currently crossing carries something like 1/10 of a particle per cubic centimeter on average, far thicker than the exhausted wind Voyager had left behind. Crossing the heliopause meant trading the sun's rule for the galaxy's. The heliosphere is an obstacle. The sun is plowing through the interstellar gas, and that gas cannot flow cleanly through the magnetic bubble, so it has to split and stream around the outside, the way a river parts around a boulder. Where a flow is forced around an obstacle, it bunches against the surface, compressed, denser there than it is far away. A layer of interstellar gas is piling up against the outer skin of the heliosphere, squeezed by the bubble it cannot enter, and Voyager, climbing outward through that compressed layer, was reading the pile-up itself. Dense, out here, only because nothing can pass cleanly through. And it is not only gas that piles up. The galaxy's own magnetic field, threaded through that interstellar gas, gets draped across the bubble and compressed along with it, adding its own squeeze to the layer. How thick that compressed layer is, and exactly where it gives way to the calm, ordinary interstellar gas beyond, we still cannot say with any confidence. Both probes were still inside it when they last returned usable readings, still measuring a density that had not yet leveled off. We have crossed into interstellar space and have not yet reached the part of it the sun has left undisturbed. It is worth holding on to just how empty this denser space remains. At 1/10 of a particle in each cubic centimeter, you would have to sweep up every speck from a cube of this interstellar gas, more than 300 miles on a side, to gather as much matter as you take in with a single breath. This is the crowded version. This is space filling back up. The thickening Voyager measured is entirely real, and it overturned the expectation completely, and it is still a vacuum so deep that nothing we have ever built on Earth has come close to emptying a room that well. What I find worth pausing on is how quietly the rules changed. There was no announcement at the boundary, no marker warning that the very meaning of getting farther out had just inverted. On one side of a thin seam, distance meant emptier, because the sun was the source and the probe was leaving it. On the other side, distance meant fuller, because now it was pressing into a pileup that belongs to the galaxy. The same direction of travel, straight outward, came to mean two opposite things, settled entirely by which side of the wall the reading was taken from. A pileup, though, should do more than merely thicken. When a gas is compressed, jammed together against something it cannot get past, it is supposed to heat, crowd the particles, and they collide more often, move faster, grow hotter. By that reasoning, the skin of the heliosphere, with interstellar gas pressed hard against it, ought to have been among the hottest places Voyager ever crossed. When the probe finally took the temperature out there, the figure it sent home made even less sense than the density had. When a fast-moving gas breaks hard, its lost motion has to go somewhere, and where it goes is heat. The energy a flow carries simply by moving does not vanish when the flow is stopped. It turns into the random jostling of particles, into temperature. A capsule falling back to Earth glows because the air it slams into converts the craft's speed into searing heat, and the same bookkeeping governs the solar wind. When that wind struck the termination shock and dropped from close to 1,000,000 miles an hour to a small fraction of that in an instant, all the motion it shed should have reappeared as a sharp spike in temperature. The models were specific. The gas just past the shock ought to have flared to something near 1,000,000 degrees. Voyager 2 crossed that shock in 2007 and took the temperature directly. The gas had heated, but only to about 1/10 of what the models demanded. 9 parts in 10 of the energy the slowing wind should have poured into heat were simply not present in the gas. The wind had plainly braked. The heat of that braking had largely gone missing. Energy does not actually disappear, which is one of the firmest rules in all of physics. So the puzzle was never whether it had been conserved, but where it had been hidden. Something at that shock had taken the lion's share of the released energy and carried it off somewhere the thermometer was not looking. The leading answer turns on a population of particles that most pictures of the solar wind leave out entirely. Interstellar space is full of neutral atoms, mostly hydrogen, carrying no electric charge. Because they are neutral, the sun's magnetic bubble cannot deflect them, so they drift straight in across the heliopause as though the boundary were not there, wandering deep into the solar system. The inflow is steady enough to leave a mark we can see close to home. The sun's gravity bends the paths of these drifting atoms, and on the downwind side it funnels the heavier ones, helium above all, into a long, dense plume, a faint cone of interstellar gas focused by the sun and detectable even near the Earth. The wall that turns back charged particles lets these neutral ones pour straight through the entire solar system. Once inside, sunlight and chance collisions tear electrons from some of them, turning the drifting atoms into charged ions. The moment an atom gains a charge, the solar wind's magnetic field seizes it and sweeps it up, accelerating it from nearly a standstill to the wind's own speed. These captured particles are called pickup ions, and they ride along inside the wind as a hot minority stirred into the cooler crowd. Though they never amount to many particles, by the outer reaches of the heliosphere they come to hold much of the wind's internal pressure. At the shock, that minority is what drank the energy. The violent braking dumped its released motion preferentially into the pickup ions rather than into the ordinary thermal protons that make up the bulk of the wind. The pickup ions came away ferociously hot. The thermal protons, which is mostly what Voyager's plasma instrument was built to measure, stayed comparatively cool. Some of the energy did not become heat at all, going instead into flinging a few particles to enormous speeds, seeding the fast particles Voyager would keep meeting further out. The energy was never lost. It was concentrated into a sparse, scorching population the spacecraft could barely register, while the thermometer faithfully reported the temperature of everyone else. Hand a crowd a fortune, and let a few people quietly pocket nearly all of it, and a survey of the average wallet will report that almost nothing happened. That is the leading explanation, and it is a strong one, yet the full accounting is still argued over. Exactly how the energy divides between the two populations, how much the pickup ions take, and how much escapes in other ways, has never been pinned down, partly because the instrument that could have measured those hot ions head-on was not designed with this question in mind, decades before anyone knew the question would matter. The heat is no longer entirely missing. It is mostly accounted for, mostly hidden in plain sight, and still not fully counted. Voyager did not hand back a tidy agreement with the models. It handed back a discrepancy, and the discrepancy proved richer than agreement would have been because it exposed an entire population of particles the simple picture had ignored. A measurement that breaks the prediction is the mission doing the one thing a model can never do for itself. All of this circled a single slippery word: temperature. Out where the gas grows this thin, temperature stops meaning what it means down here, and the place that becomes impossible to ignore is the boundary itself, where Voyager passed through gas measured at tens of thousands of degrees and took no harm at all. How can something that hot leave a spacecraft completely cold? Even after the heat went missing, the gas out there was not cool. The temperature Voyager measured beyond the boundary still ran to tens of thousands of degrees, somewhere between 30 and 50,000 on the Kelvin scale, which is several times hotter than the visible surface of the Sun. By every reading the spacecraft sent home, it was crossing a furnace fiercer than anything that exists on Earth, hotter than molten rock, hotter than the face of the Sun itself. And it took no harm at all, its instruments working on as though nothing around them had changed. A furnace that cannot warm a teacup sounds like a contradiction until you notice how loosely we usually use the word hot. Temperature and heat are not the same thing, though we treat them as one. Temperature measures how fast the individual particles of a gas are moving, the energy carried by each single one. Heat is the total energy that actually flows into something, and that depends not only on how fast the particles move, but on how many of them arrive to deliver it. Voyager does not so much feel this temperature as count it, reading the spread of speeds among the particles it meets, and a wide spread of fast motion is exactly what a high temperature is. A lone particle racing along at tremendous speed has a high temperature and almost no heat to give because it is only one. Warmth, the kind your skin knows, is a crowd of particles striking you over and over, each handing across a little energy, the deliveries piling up faster than your body can shed them. Out beyond the heliopause, the particles are moving ferociously indeed, tens of thousands of miles an hour apiece, which is just what tens of thousands of degrees means. But there are almost none of them. At a tenth of a particle in a cubic centimeter, the gas is so thin that one patch of the spacecraft might be struck by a single blazing particle and then wait a long while before the next arrives. Each impact leaves its tiny crumb of energy, and then nothing, for ages. The total warmth reaching the craft from all of them together comes to roughly a billionth of a watt on each square of its skin, while the spacecraft's own small nuclear source pours out hundreds of watts from inside. The furnace outside is real, and it is completely buried beneath the faint warmth the probe carries with it. The deeper irony is that out in this furnace, the true threat to Voyager has always been the cold. Space itself sits only a few degrees above absolute zero, and the craft steadily bleeds its warmth away into that emptiness by radiation. The long fight has never been to keep the spacecraft from overheating in the wall of fire, but to keep its fuel lines and electronics from freezing solid, which is why holding its vital parts warm enough to work is a constant quiet concern. Your own body knows this difference, even when the words for it slip. Step into a dry sauna at 90 degrees, hot enough to cook an egg, and you sit there in comfort because dry air is sparse and carries little heat. Let in a cloud of steam at a far lower temperature and it scalds you instantly because water is dense and floods your skin with energy in seconds. The same lesson lives in a sparkler. Its flying sparks burn at well over 1,000 degrees, hotter than molten iron, and they land on a child's hand without leaving a mark, because each speck is so small that all its ferocious temperature adds up to almost no heat. A fleck of metal at 1,000 degrees and a furnace at 50,000 are working the same trick. Speed without numbers cannot warm you. We say hot and picture danger, a thing that will burn, because every furnace we have ever met down here was also packed with matter, ready to pour its heat into us. Out there, the two halves of the word come apart. The space beyond the sun is dotted with furnaces hotter than the sun's own surface that could not warm a single held breath, because they hold almost nothing inside them to do the warming. The wall of fire is fire in the literal sense. It simply has no fuel to spend on you. So the heat was never the danger, and the spacecraft passed through the furnace untouched, free to go on measuring everything around it. What it found next, in the magnetic field threading that thin, hot gas, was the one result no one had braced for. Out there, beyond the wall, which way was the field pointing? A magnetic field has a direction, and out here two different fields were meant to meet. Inside the bubble runs the sun's field, dragged outward by the wind and wound into a wide spiral, pointing the way the sun's magnetism happens to point. Outside lies the galaxy's own field, the magnetism threaded through interstellar space, built by processes that have nothing to do with the sun and no earthly reason to agree with it. Two fields, two separate origins, each aimed wherever it was aimed. The expectation was clean and confident. Crossing the heliopause would carry the spacecraft out of the sun's magnetic country and into the galaxies, and the surest sign of that crossing would be the compass swinging hard. The field direction should rotate as the probe left one field behind and entered the other, the way a needle jumps when you carry it from the pull of one magnet into another's. Of every signal expected to mark the true edge, this one seemed the most certain of all. When Voyager 1 crossed in 2012, the field did not turn. The magnetism just outside the boundary pointed within a couple of tens of degrees of the magnetism just inside it, a small fraction of the near total swing that had been predicted. The compass barely twitched where it had been guaranteed to spin. The stillness was so unexpected that it nearly cost the discovery itself. Because the field refused to rotate, some scientists doubted the spacecraft had crossed anything at all, and for months, there was honest argument over whether Voyager was truly in interstellar space or still caught inside some strange pocket of the sun's domain. The crossing had to be settled by other evidence, by the collapse of the solar particles and the surge of galactic ones, because the signal everyone had trusted most never arrived. A single strange reading can always be a fluke, an instrument fooled by a local quirk. So, the real weight of it waited 6 years, until Voyager 2 reached the boundary in a different place, on a different path, carrying its own separate magnetometer. It found the same thing. The field outside lined up with the field inside, once again refusing to turn. 2 probes, 2 crossings, billions of miles apart, both stepping from the sun's magnetism into the galaxies and meeting an unchanged direction. Whatever this was, it was no accident. It was not only the Voyagers that pointed this way, either. A separate spacecraft circling near the Earth had been mapping a faint ribbon of particles streaming back from the rim of the heliosphere, a band whose shape betrays the direction of the interstellar field pressing on the bubble. The orientation that ribbon implied, measured from deep inside the solar system, agreed with the field direction the Voyagers found out at the wall. 3 instruments, by 3 different methods, were sketching the same surprising geometry. The best explanation is that we are not yet seeing the galaxy's true field at all. The interstellar magnetism no more passes cleanly through the heliosphere than the gas does. It drapes over the bubble, combed and bent around the obstacle, the way cloth pulled across a stone takes on the stone's shape near the surface while hanging freely farther off. In that draped layer, exactly where both Voyagers are still traveling, the interstellar field has been folded into near alignment with the solar field by the simple act of flowing around the boundary. The compass did not turn because the probes have not yet left the region where the 2 fields are crushed together and combed parallel. The galaxy's real, undisturbed magnetism still waits somewhere farther out, unmeasured, just like the calm interstellar gas the rising density has not yet reached. The tilt of that draped field may also be part of why the bubble is lopsided, pressing the boundary closer in on one side than the other, which would help explain why the 2 probes met the wall at different distances and different times. One surprising result quietly tugging on another. That is the leading account, and like the missing heat, it explains the result without fully closing it. Why the alignment is as tight as it is, how thick the combed layer runs, where it finally gives way to the field's true heading, all of that stays open. We crossed the line we had chased for decades and found, on the far side, a version of our own field looking back. Picture stepping across a national border, braced for a foreign language and hearing your own spoken on the other side. That was the shape of the surprise. The Voyagers left the sun's magnetic country expecting a stranger's, and the magnetism that met them had been bent into the familiar lines they carried from home. The country on the far side does not truly speak our language. We have only not yet walked far enough past the border to leave the bilingual zone where both tongues still blur together. The direction of that field held one surprise. Its strength held another. When the Voyagers measured not which way the interstellar field pointed but how hard it was pushing, the figure overturned how much force the galaxy had been bringing against our bubble all along. How hard was the galaxy pressing in? The heliosphere holds its shape by a standoff. The sun's wind pushes outward, the galaxy presses inward, and the boundary settles wherever the 2 come even. To know how large the bubble should be, and how firmly it holds, you have to know how hard each side is pushing. The push from inside, the wind, we had measured for decades. The push from outside, the galaxy, we had only estimated, and the estimate was badly low. When the Voyagers reached the interstellar field and measured its strength head-on, it came back 2 to 3 times stronger than the models had assumed, and both probes, reading it with their own magnetometers, agreed on the strength as firmly as they had agreed on the direction. That sounds modest until you follow what a field's strength does to its pressure. The pressure a magnetic field exerts climbs with the square of its strength, so a field 2 to 3 times stronger pushes not 2 or 3 times harder, but closer to 10 times harder. The galaxy had been leaning on our bubble with something like 10 times the force anyone had reckoned. This should sit strangely against what we just saw out there. The gas beyond the boundary is so thin it cannot warm a spacecraft, barely a tenth of a particle in a cubic centimeter, all but nothing. And yet it crushes inward on a bubble 11 billion miles across. Almost none of that push comes from particles striking the boundary, because there are far too few of them to matter. It comes from the magnetic field woven through the thin gas. A magnetic field is more than empty space with a direction painted on it. It carries a pressure of its own, and it resists being squeezed. Force its field lines closer together and they push back, like a bundle of springs compressed against your palm, harder the tighter you press. So, a magnetized gas can shove with real force even while it holds almost no matter at all, because the shoving is done by the field and not by the few particles riding inside it. It changes the whole picture of how the galaxy meets us. The push from interstellar space is barely a wind of gas at all. It is mostly magnetic, a pressure stored in field lines, with the sparse matter nearly along for the ride. And the magnetism doing all this is, by every standard we know, absurdly faint. The interstellar field measures about half of a nanotesla, roughly 100,000 times weaker than the field at the surface of the Earth, far too feeble to stir the smallest compass or lift the lightest iron filing. A field you could never feel, one that would do nothing whatever to a magnet on your refrigerator, is squeezing the entire solar system into shape from the outside. It manages that not by being strong but by being everywhere, pressing across a surface so enormous that even a feather's weight on each acre mounts into a siege. A galaxy pushing 10 times harder than expected means a bubble more besieged than the textbooks ever drew. The heliopause rides closer in than a gentle outside push would allow, the boundary held not in a calm equilibrium, but in a tighter, harder pressed balance. The wind from within has to labor against a stronger wall than we believed, and the whole bubble stands more compressed, its shape carved more by that outside magnetism than by the wind alone. A shell braced against a stronger field is also one more easily dented, more sensitive to every change in the galaxy it drifts through, its walls under more strain than the old calm diagrams admitted. The protective shell around the planets is real, and it is bracing against far more than anyone had counted on. An inversion sits at the center of this. The same interstellar gas that was too thin to deliver any heat, that let a furnace wash over the spacecraft as harmless as a held breath, is strong enough to crush the edge of the solar system into its shape. Thin enough to ignore, and firm enough to confine us. The galaxy barely touches us with matter. It holds us instead with a magnetism so faint we cannot feel it, and so vast we cannot get out from under it. One prediction after another had cracked open at this boundary, the wind that refused to fade, the density that rose where it should have thinned, the heat that hid itself away, the field that would not turn, and now a galaxy pressing 10 times harder than the models had sworn it could. The misses had stopped being separate surprises. When a wall of careful predictions falls this completely, the falling itself becomes the thing worth understanding. What does it mean that we were wrong about the edge so thoroughly, and so many times over? Before any of this was measured, it was drawn. The heliopause existed for decades only as a boundary on paper, sketched from equations and from the faint light of other stars, a line careful people placed using the best physics they had. They disagreed even so. The estimates of how far out the edge would lie ranged from around 50 astronomical units to well past 100. The models unable to settle even on its distance, let alone its nature. Everything we said about the edge of the solar system for 2 human generations was a description of a place no one had ever been. There was no other way to do it. You cannot lay the heliopause under a telescope. It gives off almost no light of its own, and the gas that defines it is thinner than any vacuum we can build, at energies and densities no laboratory on Earth can copy. You can model it, you can photograph the glowing arcs and shells around other stars wrapped in their own winds and assume ours resembles them. You can catch the ribbon of particles drifting back from our own boundary and reason backward from its shape. Every one of those, though, is a rumor about the place, carried secondhand. The only way to learn what the edge of the solar system was truly like was to send something there, wait the decades it took to arrive, and listen to what it found. What it found, again and again, was that the careful drawing had left things out. Not foolishly. Each miss turned out to mark a real piece of physics the model had not known to include. The heat that went missing pointing to a hidden population of particles no one had counted, the field that would not turn to a draped layer no one had pictured, the runaway pressure to a galaxy that pushes with magnetism rather than gas. The predictions did not fail because they were careless. They failed because reality was carrying ingredients the equations had never been handed. When the field refused to rotate, the first instinct of careful people was not to doubt the model but to doubt the spacecraft, to wonder whether the instrument had erred or the crossing had not really happened. We defend the picture we have spent years building. The discipline lies in eventually letting the reading win, in deciding that a single stubborn measurement from 11 billion miles away outranks the consensus drawn at home. Being wrong out here stops looking like defeat. A prediction that comes back confirmed tells you something quiet, that the ingredients you already held were enough. A prediction that breaks tells you something far more useful, that the world contains a piece you did not have, and roughly where to go looking for it. Every surprise Voyager sent home was a missing ingredient, announcing itself. The mission's worth lay less in the diagrams it confirmed than in the ones it tore up. For most of history, the far edges of every map were drawn from rumor, from sailors' second-hand reports and reasoned guesses about what must lie past the known, and those edges were always wrong in ways no one could fix from home. They were corrected only by the first person willing to sail out and walk the actual ground, and carry back word that the coastline ran another way entirely. Voyager is that first walker for the edge of the solar system. Everything before it was the rumor. The people who designed it had spent careers refining the very predictions it would go on to overturn, and they sent it anyway, knowing its most valuable readings would be the ones that proved them wrong and that most of them would not live to see which ones those were. They built an instrument to outrank their own diagrams. It is no small thing to care more about the answer than about having been right. There is an unhurried honesty in that, too. We are used to treating not knowing as a problem to rush past. Out at this boundary, not knowing was simply the truth of the situation, and the only way through it was not to argue the diagrams harder but to go and look and let the place itself have the final word over every confident line we had drawn of it. Reality outranked the map. The place Voyager walked into was never going to hold still long enough for a clean final word, though. The boundary that broke all those predictions does not even sit quietly while we study it. Its whole surface moves, rolling with disturbances larger than anything in the inner solar system. How big can a wave on the edge of the solar system get? We have been calling it a surface, a wall, a seam, as though it were a sheet pulled taut. It is nothing so still. The skin of the heliosphere is in constant motion, and not the slow, whole-body breathing that carries it in and out with the sun's 11-year pulse, but something faster and more local, ripples running across the boundary itself, swells rising and traveling and sinking along its face. The largest of them are almost impossible to hold in the mind. A single one of these waves can reach 10 astronomical units across. 10 times the distance from the Earth to the Sun, around 930 million miles, folded into one wrinkle on the surface of the bubble. That is roughly the full width of Saturn's orbit. One ripple on the edge of the solar system is wide enough to swallow everything out to Saturn, the Sun and the inner planets and the asteroid belt and Jupiter, all tucked inside the span of a single passing swell. The reason a boundary like this cannot stay smooth lies in what it actually is. It is the seam where two plasmas slide past each other, the sun's wind moving along the inside, the interstellar gas streaming along the outside, the two pressed together yet running in different directions at different speeds. The slowed wind on the inner face still slides by at well over 100,000 miles an hour, while the gas on the outer face drifts far more slowly, and a mismatch in speed that large across a thin seam is exactly what shreds a smooth surface into waves. The same physics lifts waves on a lake when wind blows across still water. The air and the water are sliding past one another, and the smallest unevenness at their boundary gets caught by the flow, raised, and drawn out into a traveling wave. On the heliopause, the wind and the interstellar gas do this to each other. Except the lake is 11 billion miles out, and the waves it raises run wider than planetary orbits. The shear is not the only thing stirring it. When the sun turns stormy, it sends pressure pulses rolling outward through the wind, and those pulses reach the boundary and shove it, denting and bulging the surface from within. Between the steady shear of the two flows and the irregular battering of solar weather, the boundary never settles on one clean shape, its waves rising at uneven angles, in no tidy pattern, a surface heaving in many directions at once. This is no ordinary surface flexing either. The boundary is a sheet of magnetized plasma, and where its folds press together hard enough, the magnetic fields on each side can snap and rejoin, pinching off islands of plasma that drift away on their own, like froth shed from the crest of a breaking wave. The edge of the solar system does not merely ripple. In places it tears, reknits, and sheds pieces of itself into the dark. These vast swells are only the largest of the disturbances. Beneath them, the boundary churns with ripples at every scale, a whole cascade of turbulence running down from orbit-sized waves to ones far too small to measure. And as that surface heaves, it alters, slightly, how much of the galaxy's high-energy radiation slips past it, so the shield around the planets does not hold perfectly steady, but flickers faintly in time with the boundary's unrest. Voyager caught that flicker directly, the count of galactic particles climbing in sudden steps and easing again as waves of boundary rolled across the probe. What makes these waves so hard to picture is not only their size but their pace. A swell 10 astronomical units across does not race. It rolls along the boundary over months and years, far too slow and too vast for anything riding inside the bubble to feel it pass. A spacecraft caught in one would have no sense of being lifted at all, the way a single speck of plankton could never feel an ocean swell 1,000 miles long. We know the waves are there only because Voyager, in crossing, found the boundary in motion, the surface moving across the probe rather than the probe simply moving across it. The word edge has misled us at every step of this. An edge sounds final and fixed, a place where things simply stop. What Voyager actually reached was a living membrane the size of the solar system, breathing on a decade-long rhythm, rippling with waves wider than the orbit of Saturn, tearing and healing along its folds, never twice the same shape. The boundary of everything the sun holds is less a line than a kind of weather, and we have caught only a few moments of it. Voyager did not only feel this restless boundary shift and push around it. As it crossed into the thicker plasma beyond, the spacecraft began picking up something stranger than motion, a faint and steady tone rising out of the medium itself. For the first time, an instrument built by human hands was listening to interstellar space. What does it sound like out there? There is no sound out there. Sound is a pressure wave passing through a crowd of molecules packed close enough to jostle one another, and the gas at the edge of the solar system is so thin that nothing can carry an ordinary sound across it. A scream out there would not travel an inch. And yet Voyager has been sending back a tone, a faint, clear pitch out of interstellar space, and the tone is real. What the spacecraft hears is not sound but the plasma itself ringing. A plasma is a gas torn into loose electrons and the heavier ions they were stripped from, and a sea of free charges like that has a voice of its own. Nudge the electrons out of place by any disturbance, and the pull of the ions they left behind hauls them straight back. They overshoot, get tugged back again, and the whole sea begins to slosh, the electrons swinging around the ions in a steady oscillation. That sloshing is the plasma's natural note, and a note has a pitch. That pitch is set by one thing alone: how densely the charges are packed. Crowd the electrons closer and the restoring pull between them and the ions grows stiffer, so they slosh faster and the note climbs. Spread them thin and the note falls. The link is not quite one for one. The pitch rises as the square root of the density, so a plasma 4 times thicker sings only twice as high. Still, the pitch of a plasma is a direct readout of how much is in it, the way the ring of a wine glass shifts as it fills, the tone telling you, without your ever looking inside, how much it now holds. Measure the frequency of that ringing and you have measured the thickness of the gas exactly. This is how Voyager now takes the pulse of interstellar space. Its own direct plasma sensor failed back in the 1980s, decades before it reached the edge, so it cannot count the particles around it one by one. Instead, it listens. 2 slender antennas, each about 10 meters long, the length of a city bus, splay out from the craft in a wide V and catch the faint electric sloshing of the plasma around them. The impossible density readings of the last few acts, the gas that grew thicker the farther out it went, were never counted at all but heard, decoded from the rising pitch of a ringing the spacecraft could register, though never truly hear with ears. When Voyager crossed the boundary and the density leapt some 20-fold, the plasma's note jumped with it, climbing about 4.5 times higher in pitch, the audible signature of the very thickening those earlier readings described. We first caught the tone by accident when the sun lent a hand. In late 2012, a burst of solar activity sent a disturbance rolling all the way out to the boundary, and when it struck the dense interstellar plasma, it rang it, the way a passing truck can set a glass humming on a shelf. For weeks, the plasma sang, and the pitch of its song, near 3,000 cycles a second, told the listening instrument that Voyager was now wrapped in gas far denser than the wind it had left behind. The crossing into interstellar space, the one the silent magnetic field had failed to mark, was confirmed by a note. 3,000 cycles a second is a pitch a person can hear, a high, thin tone near the top of a piano's range, and it happens to fall squarely in the band our ears are most sensitive to, the range tuned over millions of years to catch a cry or the snap of a twig. The plasma did not have to ring at a frequency we could hear. It simply does. And so the density of the galaxy at the limit of the sun's reach arrives already in the form of a note we can take in without changing a thing. What we hear is not sound at all, but the electric voice of a plasma, translated into the one register our hearing was built for. But years later, listening more closely, the team found the tone had never fully stopped. Underneath the loud ring set off by the sun ran a faint, continuous hum, the plasma singing on its own, with nothing obvious to strike it. What out there was ringing the plasma, steadily, with nothing to set it off? The tone the sun's burst set off should have died away. A struck glass rings and then fades, its energy bleeding into the air. And the plasma wrung by that solar disturbance should have done the same, singing for a while and then falling quiet until the next shock came along. For years, that was the pattern. The gas sang only when something struck it, every few years, when a shock happened to roll out from the sun and set it ringing. Between those events, we assumed interstellar space was silent. When researchers went back through the recordings with more care, listening beneath the loud rings, they found a far fainter tone running underneath, continuous, never stopping. A thin, narrow hum near 3,000 cycles a second, present in stretch after stretch of data where no shock had struck and nothing obvious was there to ring the plasma at all. The hum is faint almost past belief, far below the volume of the rings the sun sets off. If a shock ringing the plasma is a shout, this is the sound of its breathing between words. The interstellar gas had been singing on its own all along, quietly, without pause, with nothing striking it. A plasma ringing with nothing to strike it is a real puzzle. Some hidden source of energy out there, some unknown engine humming in the dark. The evidence does not point that way, and reaching for it would be the easy mistake. What keeps a sea of plasma faintly ringing when nothing is striking it? The likeliest answer is that the plasma is ringing with its own warmth. The electrons out there are never still. They carry the heat of that tens of thousands of degrees temperature, jittering and darting in every direction, and a sea of charges in ceaseless thermal motion is never perfectly quiet. Their random jostling sets up a faint, continuous oscillation at the plasma's natural pitch, a background hum produced by nothing stranger than the heat already in the gas. The same particle motion that defines the temperature, the motion too sparse to warm a spacecraft, may be exactly what keeps the plasma singing. This is not a guess pulled from nowhere. The same principle, a plasma faintly ringing with its own heat, is used to gauge the density of space around other spacecraft. A plasma humming with its warmth is ordinary physics. The surprise was only that the hum out here was clear enough and steady enough to hear it all. And it is a touch more steady, a touch more narrowly tuned, than the simplest picture of pure thermal jostling would predict, which hints that weak disturbances and faint instabilities in the plasma may be feeding it too. Exactly how much comes from the gas's own heat and how much from some gentle, ongoing stir is still being worked out. What sustains a faint and persistent sound? The note is not quite as fixed as steady makes it sound, either. Listen across years, and the hum drifts, slowly upward, its pitch creeping higher as Voyager presses deeper and the gas around it thickens. The rising density we met earlier is written into the slow climb of this tone, a glissando so gradual it takes years to hear, the plasma reporting its own thickening one almost imperceptible step at a time. And that continuous tone has shown the interstellar gas is not perfectly smooth. The pitch does not climb in a clean line. It rises and hesitates and rises again, tracing gentle ripples and clumps in the density, structure in the local medium at scales no one could map before Voyager was inside it to listen. For all the violence at the boundary, the shocks and the tearing and the orbit-wide waves, the gas just beyond hums on at almost a single pitch, year after year, a held note in the dark that does not break. Interstellar space, which we so often picture as the emptiest and most silent place there is, turns out never to be fully quiet. It carries a faint, constant tone, sustained by its own warmth, that has very likely been sounding since long before the sun was born and will go on long after. The sound was always there. Voyager simply traveled far enough to finally hear it. Not every tone out there rises from the plasma's own warmth, though. Some of it still comes from home. The sun's storms do not stop at the boundary. They push straight through it, carrying the sun's disturbances out into a medium that was never meant to feel them, ringing the interstellar gas from 11 billion miles away. How does a storm on the sun still shake the space beyond the sun's own edge? The sun's wind ends at the boundary. Its influence does not. Long after the wind itself has stopped, 11 billion miles out, the sun can still reach across the wall and stir the space beyond it, space that no longer belongs to the sun in any ordinary sense. It does this through its storms. When the sun grows active, it hurls off great clouds of charged gas and flares of energy, and each outburst sends a pressure pulse rolling outward through the wind, a shock front racing away from the sun in every direction. Most of the time, these fronts simply travel and weaken, but when the sun is stormy, many launch close together, and as they race outward, the faster ones overtake the slower, piling up and merging into a single broad front, a wall of compressed wind far larger than any one storm that made it. That merged front takes more than a year to cross the distance to the boundary, arriving as a delayed echo of a season of solar weather that has long since faded back home. When it reaches the heliopause, it does not stop there. The front slams into the boundary and shoves it, and the disturbance passes through into the interstellar plasma beyond, carried across the wall the way a heavy thump on one side of a shared wall is felt as a tremor in the next room. The bulk gas does not cross, the push does. On the far side, the front becomes a shock, moving out into the denser interstellar plasma, slower now and reshaped by the thicker medium, but still a pressure wave from the sun rolling through gas the sun's wind can no longer reach. And as it goes, it rings that gas, setting the electrons sloshing at their natural pitch. The loud tones Voyager first heard, the ones that revealed the density of interstellar space, were exactly this: the sun's storms reaching through the boundary and striking the gas outside it like a mallet on a drum. The ringing was not the only mark these fronts left. As each compressed front swept past the spacecraft, it briefly brushed aside some of the galactic cosmic rays streaming in from deep space, and Voyager's counters caught a sudden dip in those particles, a shadow passing over and then lifting. A storm on the surface of the sun, more than a year earlier, was casting a measurable shadow across a spacecraft already outside the solar system. These were not single events. Over the years after the crossing, Voyager caught one after another, a recurring drumbeat of solar fronts arriving roughly once a year through the sun's active stretches, each ringing the gas and dimming the cosmic rays in turn. Before the faint continuous hum was ever found, these arrivals were the only times the density could be read at all, the boundary speaking up once a year when the sun happened to knock. The sun is not the only thing that sends shocks through this medium. The space between the stars is a shared sea, and far greater disturbances cross it. The shock waves of exploding stars, supernovae sending fronts rolling across hundreds of light years, a reach beside which the sun's whole 11 billion-mile domain is a single footstep. The pulses Voyager hears from the sun and the vast fronts from dying stars are the same kind of thing at wildly different scales. The local whisper and the distant roar traveling through one continuous medium. The sun's storms are only the nearest and faintest voice in a sea that carries the shouts of exploding stars. We drew the edge of the solar system at the place where the sun's wind gives out, and called everything past it no longer the sun's. Yet the sun still touches that space, still rings its gas, still throws its shadows across particles a year's travel beyond the wall. Influence does not end where territory ends. The sun's reach, the true extent of what it can still affect, runs well past the border we drew for it, fading not at a line but by slow degrees out into a darkness it no longer rules and has not entirely left. And it has always done this. Every storm the sun has thrown, for billions of years, has sent its faint pulse past the wind's edge into the gas beyond. The sun has been whispering into interstellar space for its whole life. We simply had nothing out there to hear it until now. So the sun presses outward through the boundary, while the galaxy presses inward against it, two influences meeting and overlapping at the same thin seam. That seam is not a clean dividing line with one world on each side. It is a place in its own right, where the two media touch and blur, belonging fully to neither. What is it like in the layer that is neither inside nor out? We keep speaking of two sides, the sun's plasma within and the galaxy's plasma without, parted by a single wall. There is no single wall, and no clean pair of sides. Between the fresh solar wind and the calm, true interstellar gas lies a whole stack of in-between regions, each belonging fully to neither, and the boundary we have been chasing all this time is really this entire blurred thickness. Coming from inside, the wind first strikes the shock where it breaks and heats, then enters the heliosheath, a turbulent zone of solar wind that has been stopped and turned, some 30 astronomical units deep, billions of miles of wind that is no longer streaming yet, not yet anything else. Then comes the heliopause, the thin membrane itself. Beyond it, the gas is not the quiet interstellar medium either. It is the piled-up, compressed, magnetically draped layer we met before, interstellar in origin but bent and stirred by the bubble it leans against. On both sides of the membrane, the plasma sits in some halfway state, neither the pure thing it came from nor the pure thing it is becoming. The membrane itself is a selective filter, and that is the key to how the two worlds touch. It is nearly sealed to charged particles, turning back the ions and electrons of the interstellar gas, holding the solar wind in. But to neutral atoms, the ones carrying no charge, it is wide open. They drift straight through as though it were not there. That openness allows a strange kind of mixing, one that happens a single atom at a time, by a trading of identity rather than any blending of fluids. A fast proton from the solar side meets a slow neutral atom drifting in from interstellar space, and in the passing the proton steals the neutral's electron. Their roles swap in an instant. The fast solar particle, now neutral, flies off in a straight line at the wind's own speed, hundreds of kilometers a second, uncoupled from every field, free to cross the boundary as though it had dissolved. The slow interstellar atom, now charged, is seized by the local field and swept up. It is the strangest sort of crossing, no current of gas passing through at all, only a swapping of who is who. This single quiet process is the hidden thread running through nearly everything Voyager found out here. The pickup ions that drank the missing heat were interstellar atoms that traded their neutrality for a charge and were caught by the wind. The ribbon of particles that let a spacecraft near Earth map the far-off field was built from fast atoms that had swapped identities at the seam and come streaming back inward, undeflected, carrying the imprint of the boundary where they were born. The whole shape of the edge was mapped, from inside the solar system, by catching the atoms it had traded, the seam made visible by its own exchanges. The seal is imperfect in one more way. Voyager found a thin scattering of particles from inside the heliosphere leaking out just past the boundary, slipping along magnetic field lines that thread briefly across the seam and faint traces of the interstellar side reaching just within. The wall holds, for the most part. It is porous at the edges, letting a little of each world bleed into the other. The nearest thing to it on Earth is the mouth of a great river, where it broadens into the sea. There, the fresh water and the salt do not meet at a clean line. They interleave in shifting layers, fresh riding over salt, mixing along their contact in slow curls, and the long brackish stretch that results is neither river nor ocean, but a distinct place with its own chemistry and its own life. The seam at the edge of the solar system is that estuary written in plasma, a broad brackish zone where the sun's sea and the galaxy's sea lean into each other and trade, belonging to neither. The real boundaries of the universe are rarely the lines we draw of them. A line is a convenience, a place to set the label. The actual edges are almost always zones, thick and gradual, where one thing becomes another by degrees, and the two genuinely overlap. There is a feeling everyone knows that lives in the same shape, the drift each night between waking and sleep, a stretch that is not quite either, where the day has not fully let go and rest has not fully arrived, crossed not in a moment, but over a span. The edge of the solar system is a threshold of that kind, an honest in-between, and Voyager is somewhere inside it even now, in the brackish dark, neither home nor truly away. This whole elaborate seam, the shock and the sheath and the membrane and the brackish layer beyond, has been doing one thing for us all along, whether or not it was ever meant to. It holds back the full force of the galaxy. Everything inside it, every planet, every living thing that has ever drawn breath has spent its entire existence sheltered behind this boundary. What exactly has it been keeping out? When Voyager crossed the boundary, one number rose instead of falling. The count of high-energy particles arriving from the wider galaxy climbed sharply the moment the spacecraft left the bubble, and for the lower-energy ones the jump was larger still. Inside, the count was held down. Outside, the full galactic flood. The gap between those two numbers is the measure of a shield, and that shield is the whole reason the inside is calm. The particles raining in from the galaxy are nothing like the thin, warm gas we met before. Those were sparse and slow enough to be harmless, a furnace with no fuel to spend. Where that plasma was warmth, these are bullets, single nuclei flung out by exploding stars and other violences across the galaxy, driven to within a hair of the speed of light, each one carrying a ferocious load of energy. The rarest of them arrive with the energy of a hard-thrown baseball packed into one atomic particle. A single one striking an instrument registers as its own distinct event. A particle like that tears through whatever it meets rather than warming it. Moving near light speed and carrying a charge, it rips electrons from every atom along its path, leaving a narrow trail of broken molecules through anything it crosses. Through living tissue, that trail cuts across the long molecules that carry a cell's instructions, snapping strands of DNA, scrambling the chemistry a body relies on to copy itself faithfully. A steady, heavy rain of these would mean a steady, heavy rate of damage, mutation piled on mutation faster than any cell could mend. The heliosphere is the outermost wall against that rain. The sun's wind and the magnetic field woven through it push back on the incoming particles, scattering many and turning the lower energy ones away before they ever reach the planets. The lowest energy galactic particles are shut out almost entirely. Only the most energetic punch their way into the inner solar system at all. It is not the only shield. Closer in, the Earth's own magnetic field deflects more of what slips through, and the atmosphere overhead absorbs nearly all the rest, soaking up as much radiation as a wall of concrete some 4 meters thick. Life on the ground sits at the bottom of a nested set of shelters, and the heliosphere is the first and largest, the outer rampart that thins the flood before the inner walls finish the work. It does not even hold steady. The outer shield breathes with the sun's 11-year cycle, pressing harder against the rain when the sun is active and easing when it quiets, so the radiation dose in nearby space rises and falls in time with the sun's temper. This is why a crew bound for Mars, months beyond the Earth's magnetic field, would face cosmic radiation as one of the gravest hazards of the journey, stepping out from under the inner shelters into the thinner protection of the heliosphere alone. The danger of deep space is not the cold or the warmth, it is this rain. Even at the bottom of all those shelters, the rain is not entirely stopped. Right now, indoors, in the dark, a soft and ceaseless sleet of particles is passing through your body, thousands of them every minute, the faint survivors of cosmic rays that began as the shrapnel of distant stars. They pass through you mostly without harm, too few and too scattered to matter, caught and thinned by shield after shield on the way down. That gentle trickle is what remains after the heliosphere has already turned away the greater part of the flood, 11 billion miles out. What is hardest to take in is how long this shelter has stood. The sun has blown its wind and held up its bubble for as long as it has been a star, billions of years, far longer than there has been any life on Earth to shelter. Every organism that has ever lived, every cell that has ever divided, the first faint films of life in the early oceans and every creature since, has done so beneath this same roof, never once in a day without it. Life did more than survive under the shield. It took shape under it, its very machinery for copying and repairing itself calibrated against the small dose that gets through, no more and no less. We are, in the most literal sense, built to live inside this bubble. There is something strange in protection this complete. The most important shelter in our existence is one we have never felt, never seen, never had to think about for a single moment of our lives. It asks nothing of us and announces nothing. We learned it was even there, and learned how much it does, only by building a machine and sending it far enough out to step beyond the roof and measure the storm on the other side. The shield was always over us. It took Voyager leaving it to show us we had been sheltered all along. This roof of ours is not alone in the dark either. The whole heliosphere, with everything it guards, sits inside a far larger emptiness, a vast bubble blown not by the sun but by the deaths of other stars. We are sheltered within a shelter within a shelter. What carved the great hollow that holds us? Step back far enough and the heliosphere vanishes entirely. The bubble that took Voyager 40 years to cross, 11 billion miles of it, shrinks to a speck because the sun and its whole protective shell are sitting inside something vastly larger. A cavity in the galaxy, a stretch of space scoured nearly empty, roughly 1,000 light-years across. We call it the local bubble, and we sit very near its center. If the heliosphere were a basketball, the local bubble would be a hollow some 60 kilometers across, with that basketball drifting near the middle. Everything Voyager has ever done, every mile of its impossible journey, has happened within the first few inches of that basketball, while the true cavity stretches away unseen on every side. The hollow was not always here. It was carved, blasted open over the last 10 to 15 million years by a series of dying stars, perhaps a dozen or more, each one a supernova flinging its outer layers outward at a fraction of the speed of light. Those blasts swept the interstellar gas ahead of them, piling it into a dense shell at the cavity's edge and leaving the inside hot and thin and nearly clear. The space we live in is the cleared aftermath of a string of stellar deaths. We are not guessing this from theory alone. The explosions left physical traces, and some of them fell on Earth. Buried in the deep ocean floor, in layers laid down a few million years ago, sit faint deposits of a radioactive form of iron, iron-60, made almost only in supernovae and found nowhere it could have come from on Earth itself. It rained down out of the sky, the fallout of nearby stars that had detonated within reach, settling into the seabed where it has been slowly decaying ever since. The same explosions that hollowed out the space around us left a thin dusting of themselves in the rock of our own planet. The dense shell those blasts swept up, the rim of the cavity, is where the next generation of stars is now being born. Pile interstellar gas thick enough, and gravity takes hold, drawing it into clumps that collapse and ignite, and nearly all the young stars and stellar nurseries near us lie strung along the surface of this bubble, on the very shell the explosions raised. It has the shape of a clearing burned open in a forest, where the fire that emptied the center scorches a rim of ground, and it is along that scorched rim, in the churned and gathered debris, that new growth first takes hold. The deaths that hollowed out our quiet emptiness are the same deaths now lighting fresh stars around its edge. The inside of the bubble, where we sit, is a strange kind of empty. The gas here was heated by those ancient blasts until it glows faintly in X-rays, a soft glow that fills the whole sky, one we detected from Earth long before we understood we were sitting inside its source. The cavity is still slowly growing, its swept-up shell creeping outward even now, and the gas within it is perhaps 100 times thinner than the galaxy's ordinary interstellar medium, so sparse that our view outward is unusually clear. A great deal of how far and how cleanly we can see into the universe, the very transparency of our night sky, comes down to the accident of living inside a blown-out hollow rather than in the thick of the galaxy's gas. The shelters nest one inside another. The sun moves through a small, slightly denser cloud of gas adrift within the great cavity, and inside that cloud the sun blows its own small bubble, the heliosphere, and inside that sits everything we have ever known. A bubble within a cloud, within a hollow, within a galaxy, each scale shaped by a different force, each one we never feel. None of this is our home in any settled sense. The sun did not form in this cavity. It came as a latecomer, neither the hollow's maker nor its native, drifting in only a few million years ago on its long, slow orbit around the center of the galaxy, to find the place already cleared and waiting, made ready by explosions that finished long before there was anyone here to be sheltered. And it will not last. The same orbit that carried the sun in will carry it on, out of the center and eventually toward the crowded shell and beyond, over millions of years to come. For most of this story, our place inside these bubbles has looked like a fortunate backdrop, a calm setting that let life get on with the slow business of arising. The quiet of our corner of the galaxy may be more than backdrop, though. It may be a reason we are here at all. What if we exist because it is calm? The sun is not anchored anywhere. It orbits the center of the galaxy, carrying the whole solar system with it, and one full circuit takes about 230 million years, a span so vast that in the few 100,000 years our species has existed, the sun has traveled barely 1,000th of one turn. As it goes, it does not glide along a smooth, unchanging track, but rises and sinks through the crowded central plane of the galaxy every 30 million years or so, drifting in and out of the denser lanes where the spiral arms gather their gas and their young, violent stars. The calm, empty hollow we explored a moment ago is not somewhere the sun lives, but somewhere it is passing through. This matters because of something Voyager taught us directly. The size of the heliosphere is set by a balance of pressures, the sun's wind pushing out and the surrounding gas pushing in, and we now know the outside push can be far stronger than anyone had guessed. In the thin gas of our present hollow, the bubble swells wide and the shield holds far out. Should the sun drift into a denser region, the rising pressure outside would squeeze the heliosphere smaller, drawing the shield inward and letting more of the galaxy's hard radiation reach the planets. The densest clouds drifting through the galaxy carry thousands of times more gas than our present hollow, and in the most extreme of them, the models suggest the bubble could be compressed dramatically, pressed in toward the planets themselves. A denser, more crowded stretch of the galaxy is dangerous in more ways than one. The spiral arms are where massive stars live fast and die in supernovae, so passing through them raises the odds of an explosion near enough to matter. The same dense gas can disturb the distant shell of comets at the solar system's gravitational edge, nudging them loose to fall inward in long showers. A passage through the crowded lanes would be, in principle, a passage through compressed shielding, closer explosions, and stirred-up comets all at once. A tempting and unproven idea attaches itself here, and it deserves to be kept at arm's length. Some researchers have proposed that the timing of the sun's passages through these dense regions lines up with several of the great mass extinctions in Earth's history. The suggestion is that when the sun crossed into harsher territory, the combined stresses pressed hard enough on the living world to help tip it toward collapse. It is a striking idea, and a weak one. The dating of those ancient crossings is deeply uncertain. The statistics tying them to extinctions are thin and disputed, and most of the great extinctions have causes much closer to home that need no help from the galaxy at all. The correlation may be real. It may just as easily be a pattern we have drawn across scattered points, because we are so very good at finding patterns. Our safety is a phase. The deep quiet of this corner of the galaxy, the emptiness that gave us clear skies and a wide, strong shield, is a passing condition of a sun in transit, not a permanent feature of any home. Even our recent past is less calm than it feels, the fallout of nearby exploded stars laid down in our own seabed only a few million years ago. We arrived in still water not because the galaxy is a still place, but during a passing lull. Picture a small boat that has drifted, over hours, from rough water into a stretch of glass-flat calm, and will drift on, over more hours, into rough water again. A passenger who woke in the middle of the calm, having felt neither the current behind nor the one ahead, could easily believe the whole sea was this still. We are that passenger. The sun's passage through this quiet hollow takes so long, and our lives run so short against it, that the calm looks total and permanent when it is only the middle of a crossing, rougher water lying at both ends, millions of years behind and millions ahead. There is a way to hold this that is not frightening. The changes are real, but they move on a clock so vast that no person, no nation, no civilization we can picture will ever feel the sea turn. The rougher water ahead lies tens of millions of years off, beyond every horizon a human being has ever needed to worry about. What the knowledge offers is not dread but proportion, a true sense of the moment we occupy, a calm stretch on a long crossing, and the quiet understanding that this calm was never owed to us and is no less worth resting in for being temporary. All of this is mortality written at the scale of a star, slow beyond any feeling. Out at the edge, though, in the dark Voyager has been mapping. A much smaller and much nearer ending is already underway, one we can watch unfold year by year. The spacecraft that carried us all the way out here is dying. What does it look like for it to go? Voyager is running out of power, and it has been, slowly, since the day it launched. Its electricity comes from a few kilograms of plutonium, sealed away and giving off a steady heat as it decays, a heat quietly turned into current. The plutonium fades on a clock of its own, losing half its strength over about 88 years. And yet it is not even the main problem. The devices that convert its heat into electricity have worn down faster than the fuel itself. Between the two, the spacecraft loses close to 4 watts every year, a little less to work with each time the seasons come around. 4 watts a year sounds like nothing until you remember how little there was to begin with. Voyager launched with a few hundred watts, about what a handful of household bulbs would draw, and nearly half of that is already gone. For decades, the engineers have managed the shrinking supply like a household budget in a hard winter, switching things off one at a time to keep the rest alive. The cameras went dark back in 1990, their last picture already taken. Heaters were shut down, leaving instruments to run far colder than they were ever built to survive. The strange grace of it is that they kept working anyway, the old hardware tougher than its own rated limits, performing in a cold that should have stopped it because the engineers of the 1970s had left so much margin. In recent years, the cuts have gone deeper still, an instrument left running at temperatures tens of degrees below anything it had ever been tested for, and still it answered. What remains now is a triage. The instruments that studied the planets were the first to go, useless once the planets fell far behind. The ones kept alive longest are the few that still send back what no other machine can, the senses that read the plasma, the magnetic field, the cosmic rays of interstellar space. Each year the budget shrinks, and each time it does, someone has to choose which of the spacecraft's remaining senses to switch off next, which faculty it can least afford to lose. The death of Voyager is not a single failure, but a sequence of small, deliberate goodbyes. It has the shape of a house in a long, cold winter with the fuel running low. Room by room, the lights go off and the doors close to hold what heat is left, the household drawing into fewer and fewer rooms until all that remains is gathered around a single lamp. Voyager is in the last rooms of that house now. One by one, its lights have gone out, and the day is coming, within just a few years, when there will not be enough power to run even one instrument. Not long after, there will not be enough to work the radio at all, and every year the signal it can manage grows fainter, the same signal that already reaches Earth as less than a billionth of a watt, harder to catch as the power behind it thins. When the power finally fails, the spacecraft will not break or fall. Its plutonium will go on giving off its faint warmth for decades more, a body still warm long after it has gone silent, drifting onward at full speed through interstellar space, intact, simply unable to speak or sense or be reached. Voyager will not end so much as fall quiet. There is something I had not expected to feel about a machine. We are watching a made thing die, the way living things rarely get to, slowly, with warning, its keepers deciding with care what to surrender and what to hold on to for as long as they can. A small team still tends it, some of them having spent their whole working lives in its company, sending the commands that turn off one more heater, listening for the answer that says, "It is still there." They are keeping a long vigil, and they have known for years how it ends. The dignity in it is not that the ending is being prevented, but that it is being met, attended, and seen all the way through. There may be a kind of peace in an ending like that. Not a sudden loss, but a slow and accompanied one. A thing that did far more than it was ever asked to do, allowed to wind down gently, and kept company to the last. Most things in the universe end with no one watching. This one will not. The ending of the power, though, is not the ending of the journey, and the gap between the two is where the next strangeness lives. The radio will fall silent long before the spacecraft stops moving. Voyager will keep traveling, keep crossing into places no instrument has ever been, for thousands upon thousands of years after the last word reaches us. What becomes of everything it will witness once there is no longer any way to tell us? Everything Voyager has shown us about the edge has left a question hanging just past its reach. The density of interstellar space was still rising when we last heard, never settling to its calm, true value. The galaxy's magnetic field was still combed into alignment with the sun's, not yet pointing the way it truly points. Both of those answers, the real thickness of the gas and the real heading of the field, lie a little farther out. In the undisturbed interstellar space the spacecraft has not yet reached. Voyager is going to reach it. It is just very unlikely to still be speaking when it does. The radio will fall silent within a few years, somewhere near 170 times the Earth's distance from the Sun. The calm, true interstellar medium may lie tens of astronomical units beyond that. Decades of travel further on, perhaps more. In all likelihood, Voyager will cross out of the disturbed boundary layer and into pristine interstellar space, the very place that holds the answers we have chased through this whole story, years or decades after the last signal we will ever receive. It will arrive at the answer with no way left to send it. The continuous tone we learn to listen for, the hum climbing slowly as the gas thickens, will simply stop one day, mid-rise, cut off before it ever reaches the steady note that would mean the probe had come at last into the true interstellar sea. This opens a strange gap between two things we usually treat as one, an event happening and an event being known. When the power dies, Voyager does not stop being somewhere. It will go on physically immersed in interstellar space, the real field threading through it, the true density of the galaxy pressing on its silent hull, crossing thresholds and passing through structures exactly as it does now. All of it will happen. None of it will become anything we can know. The spacecraft will be present at discoveries that never become discoveries, witness to 100 things with no instrument awake to register them and no voice left to carry them home. And the thresholds keep coming. Within a few thousand years, the Sun, and Voyager with it, will likely drift out of the small, warm cloud it now moves through and into a different patch of the local bubble. A real change in the interstellar weather the probe will pass straight through, unsensing. Farther on waits the great shell of comets at the gravitational edge, and beyond that, the open galaxy. Voyager will travel through all of it, a working body with dead senses, the way a sleeper's eyes move beneath closed lids through rooms no one else will ever see. The nearest picture I can find for it is a traveler who keeps walking long after the last letter home has been sent. The road goes on, into country no one has mapped, and the traveler sees all of it, the turns and the rivers and the far ridgelines. But the letters have stopped, the paper run out, and so every new thing seen from here on is seen by one pair of eyes alone, carried back to no one who waited. The walking continues after the letters stop. Only our share of it ends. We carry a quiet assumption that knowledge is out there waiting to be gathered, that whatever happens leaves a mark we could find if we only looked. Most of what the universe does is nothing like that. Almost everything that has ever happened with nothing there to witness it, and was gone when it was over. Voyager spent 47 years as a rare exception, a thing that went to unwitnessed places and sent word back. Now it is being handed, slowly, back into the ordinary condition of the universe, where things simply occur and are not recorded and pass. It is not losing the journey, only the telling of it. There is no fixing this, and perhaps nothing to fix. The discoveries that never come home are not made smaller by going unheard. The gas out there will be exactly as thick as it is, the field pointing exactly where it points, the thresholds crossed exactly when they are crossed, whether or not a single instrument is awake to mark the moment. The universe does not require an audience to go on being itself. That silence is still a few years off, though, and it will not arrive all at once. Even now, while Voyager still speaks, the conversation is growing harder to hold, the words slower, the gaps longer, the day drawing closer when someone will send a command and not remain in their post long enough to be sure it ever landed. What is it like to say the last thing into a silence that answers so late? Every year, Voyager pulls farther away, and the time its words take to reach us stretches with the distance, the one-way journey lengthening by roughly half an hour with each passing year. Ask the spacecraft anything today, and the soonest an answer can return is 2 days later. In a few more years, it will be longer still. The gap that was always part of talking to Voyager is widening even as we speak. Every signal we receive from Voyager left it the better part of a day ago. We have never heard the spacecraft as it is, only as it was, a full day back in its past. So when the final signal comes, the last word we will ever receive, it will have been spoken by a Voyager that, by the time it reaches us, may already have fallen silent. We will be listening to its last word after it has already stopped speaking. What finally ends the conversation, though, is not the distance but the voice itself failing. Voyager's signal already arrives at Earth almost unimaginably faint, weaker by the time it gets here than a billionth of a watt, so weak that catching it at all takes the largest radio antennas ever built, straining to lift a whisper out of the cosmic static. Already the words come slowly, a trickle of data thinner than the earliest home modems, and as the power drops, even that trickle will narrow toward nothing. The whisper thins further every year, until it slips below even what those great dishes can separate from the noise. Power, not distance, will end the talk. There may not even be a clear final word. Endings like this rarely come with a clean last message. More often, there is simply a last good contact, ordinary at the time, followed by an attempt that brings back nothing, and then another, and then the slow acceptance that the silence is permanent. The last word is usually only known as the last in hindsight, weeks or months later, once enough silence has gathered behind it to be sure. Somewhere in the next few years, a perfectly routine exchange will turn out, with no one aware of it at the time, to have been the final one. We will not lose Voyager. The spacecraft will still be there, whole, drifting on at full speed, its warm plutonium heart still ticking. What ends is only our contact with it, the thread of words running back and forth across the dark. We will lose the conversation, not the traveler. We will lose our ability to hear it while it goes on existing, every bit as real as before, somewhere we can no longer reach. It has the feel of calling across a canyon that widens as you speak. For a long time your voice carries, and the answer comes back, late but sure. Then the far wall draws farther off, and your own voice returns to you fainter and fainter, until one call goes out and nothing comes back at all, and you are left not knowing whether the other side is empty or has only grown too far to hear. The canyon does not close, it only grows too wide for a voice to cross. There is a particular steadiness in the people who will tend this to the end. They have spent careers speaking into a delay they cannot hurry, sending words across a gap that promises no quick reply, learning to wait out the long silence between every question and its answer. That patience was a kind of practice, it turns out, for the last silence, the one that does not lift. They will send their commands knowing the window is closing, knowing that one of these days a word will go out and no answer will ever come, and they will keep sending anyway, attending the conversation all the way to its natural end. We are used to conversations that answer back at once, and we mistake that speed for the whole of what talking is. Voyager's keepers have practiced the older, slower thing, sending words out with care into a silence, trusting them to the dark whether or not an answer ever returns. The last word, whenever it comes, will close our part of the story. Voyager's own goes on far past it, into a stretch of time so vast that the entire mission, every discovery, and every silence is only its first small step. Where does it go in the deep time after we stop listening? Voyager is not going to stop. There is nothing out there to slow it, no air, no friction worth the name, so the speed it carries now is very nearly the speed it will keep forever. Long after the last signal, long after the power is gone, the spacecraft will go on coasting outward at close to 1,000,000 miles a day, exactly as it does tonight, into a future so long that the entire mission so far is only its opening instant. The first stretch of that future runs through the outermost belongings of the Sun. In about 300 years, Voyager will reach the inner edge of the great shell of comets that marks the Sun's true gravitational limit, and it will spend something like 30,000 years drifting through it before passing beyond into open interstellar space. 30,000 years simply to clear the last faint outskirts of the solar system, and the comets out there are strewn so thinly across so much room that Voyager will almost surely never come within sight of a single one. Then comes the long emptiness between the stars, and the first one Voyager draws near to lies almost unthinkably far off in time. In roughly 40,000 years, Voyager 1 will pass within about a light year and a half of a small, dim star called Gliese 445. Its twin, on its own road, will pass a similar distance from another faint star, Ross 248, in about the same span. These encounters are projections, read from the present motions of the probe and the stars, and across 40,000 years, even those motions blur, so the distances are estimates more than appointments. Even so, a light year and a half is no arrival. It is thousands of times farther than everything Voyager has crossed in all its decades. The probe will not visit these stars, only drift through their wide neighborhood, a silent mote passing in the dark. 40,000 years is the hard part to hold. Turn the same span backward instead of forward. 40,000 years ago, our ancestors were painting animals on cave walls by firelight. The last of the Neanderthals had only just vanished. Farming lay nearly 30,000 years in the future, and writing some 35,000. Everything we call history, every empire and language and book, fits several times over inside the gap between now and Voyager's first close pass of another star. The whole of the human record is shorter than the spacecraft's first errand between the stars. Across a span like that, almost nothing human survives unchanged. A spoken language drifts beyond recognition in about 1,000 years, so that the English of 1,000 years ago is already a foreign tongue to us. 40,000 years is 40 times that distance. Room enough for every language now spoken to be born, flower, and fall silent many times over. The nations that built and flew Voyager will almost certainly be gone, their borders redrawn past recognition, and the species that made it may itself have changed into something its makers would not know. Voyager will very likely still be coasting, intact, through all of it, worn so slowly by the thin interstellar dust that it could stay recognizably itself for hundreds of millions of years, perhaps longer than the Earth holds its present face. The nearest thing I can set it beside is a message in a bottle, sealed and dropped into a current, still drifting long after every shore that knew its sender has changed beyond knowing. The bottle outlasts the hand that threw it, the harbor it left, the language of the note inside, the country whose coast it sailed from. It keeps moving on the current, indifferent to all of it, carrying its small sealed cargo into waters no one who sent it could picture. Voyager is that bottle, thrown not into an ocean but into the galaxy, and the current it rides is the slow turning of the Milky Way itself, which will carry it around the galactic center for billions of years to come. Voyager has, in a sense, already left human time. It is passing out of the scale of careers and lifetimes and nations into the scale of geology and galaxies, where things are counted in the turning of the whole Milky Way. It is no longer quite ours. We made it and launched it, and we will lose the thread of it within a few years, and then it simply goes on, belonging to the deep time it has entered. There is something steadying in that, in knowing that a thing we built with our hands will outlast not only us, but nearly every trace that we were ever here, carrying on quietly through a future we cannot follow. And it does not go empty-handed. Bolted to the side of each probe is a deliberate message, a thing placed there on purpose, meant to be found by whoever or whatever might one day cross its path in that unimaginable future. Someone, decades ago, decided what an entire world should say to the dark. By what right did we speak for everyone? On the side of each Voyager rides a gold-covered disc, sealed under a cover, built to endure. In plain terms, it is a portrait of humanity, a gathered message meant to introduce our species and our world to whoever might one day find the spacecraft adrift in the deep future. Sounds of Earth, images of living things, greetings, music, even words from heads of state speaking for the planet, and etched onto the cover, a map showing where in the galaxy the sun can be found. A portrait and a return address. Set aside how it was made and what exactly is on it, and look only at the deeper fact of the thing. A small group of people, perhaps half a dozen at its core, working in one country in the 1970s, decided what an entire species would say to the universe. They chose, on behalf of 4 billion living people and every human who would ever come after, what we are, what we sound like, what we would want a stranger to know of us. None of those 4 billion were asked. None of the billions since have been asked. And because the disk is built to survive for perhaps 1 billion years, that one curated portrait is fixed, frozen, unrevisable, the single image of humanity that whoever finds it will ever receive. By what right does anyone speak for everyone? There is a strong case that the gesture was right. Someone had to decide, or nothing would have gone at all. And a thoughtful group, acting in good faith, is about as fair a way to choose as any. They never claimed a mandate. They argued among themselves over what belonged on it and could not fully agree, knowing better than anyone that no 6 people could honestly stand in for a species, and they offered the result humbly, as a gesture of goodwill rather than an official word from Earth. A hopeful hand reached into the dark costs little and means something, whether or not it is ever taken. There is an equally strong case that it was an overreach. No one elected these people to be the voice of the species. The portrait they sent is shaped, unavoidably, by who they were and where and when they lived, carrying the assumptions and the blind spots of one culture at one moment, presented as though it were simply humanity. And it was deliberately flattering. The darker truths of our kind, the wars, the cruelty, the harm we do one another, were largely left out, so that what sails into the future is not a true account but our best face, an idealized self-portrait passed off as a likeness. A stranger who found it would meet a humanity that has never quite existed. And there is the return address. The map etched on the cover points the way back to us, and no one in the 1970s, and no one now, was asked whether we wanted our location carried into the dark for anyone to read. The danger is almost certainly negligible. The disk slow, the galaxy enormous, the odds of its ever being found vanishingly small. The principle is not nothing. Even so, a handful of people decided, for all of us and all our descendants, to set down where we live. The image that fits it best is one person answering a knock at the door of a large house where everyone else is asleep. They speak to whoever stands outside on behalf of the whole household, describe the people within, offer a welcome, hand over the address, and the sleepers never wake, never know a word was said for them, never get to agree or object. Perhaps the one who answered spoke beautifully and well. Perhaps they said exactly what the household would have wanted said. The sleepers still never chose them to speak and can never take it back. We are the sleepers in that house. So is everyone who will come after. Underneath the particular choices lies a harder problem no committee could have solved. There is no neutral portrait of a species, no view from nowhere. Any message at all is a selection, and every selection is somebody's. To represent everyone is, in the end, impossible, which may be why the question of who had the right to try is so difficult to set down. There may be no clean answer, and the weighing of it belongs to you as much as to anyone, and more than it does to me. Both cases are real. Both are strong. The gesture was either a moment of grace or a quiet overreach, or, most likely, some uneasy mixture of the two that never fully resolves into one or the other. What is certain is only this: it has already been done, it is already on its way, and it can never be called back. Set the message aside, then, and the gold disc, and the question of who had the right. Turn from everything we chose to send outward to something we never chose at all, something that was simply given, the shield we have sheltered behind this whole time. We have asked what it has kept out. What would have become of us if it had never been there at all? We have spoken of what the shield keeps out. The harder way to see it is to take the shield away and ask what changes. Voyager gave us the numbers to do exactly that, since it measured both sides of the wall, the reduced flux within and the full galactic flood beyond, and the gap between them is the size of the protection. So picture the bubble simply gone and the whole flood pouring in. The first thing to be honest about is that the Earth would not instantly go dark. Even with the heliosphere gone, our planet keeps two more shelters of its own, the magnetic field wrapped around it and the thick blanket of air above us, and the atmosphere alone absorbs as much radiation as several meters of solid concrete. A person standing on the ground would not be struck down. The surface has its own armor, and it would hold most of the rain off whatever the sun's bubble did. The danger of a missing shield is quieter than that, and it runs deeper. Without the heliosphere, the whole inner solar system would sit in a far heavier rain of high-energy particles, and the top of our atmosphere would take a steadily larger dose, year upon year, across the entire long history of the planet. A little more radiation slips through any armor, and a steadily higher flux outside means a steadily higher trickle reaching the ground, the air, the oceans, and the living things in them, never enough to kill outright, but always there, always lifting the background level against which every cell must keep its chemistry intact. Life did not simply endure the radiation that gets through. It was shaped by exactly how much gets through. Every living thing carries machinery whose whole task is to find and repair the damage radiation does to its genes, and that machinery is tuned, precisely, to the dose this sheltered world delivers, and no more. Raise the dose, and you raise the rate of damage, the rate of mutation, the rate at which the instructions of life are scrambled faster than they can be mended. We already see the rule at work down here. A microbe like Dinococcus shrugs off doses that would kill a person thousands of times over by keeping spare copies of its genes and repairing the breaks almost as fast as they land, while the large and the complex have no such armor. Radiation favors the simple. Complexity needs calm. A world bathed in the full galactic flood might still hold life of some hardy, simple kind. It is far from clear it could ever have built anything like us. The shield is not a luxury laid over a life that would have managed anyway, but part of the reason this particular kind of life, large and intricate and slow, was ever possible at all. The low, steady radiation of a well-sheltered world, the heliosphere, its outermost layer, is one of the quiet preconditions written into what we are. And the dose has not even held perfectly steady across the ages. When the shelter thinned, the rain grew heavier for a time, and life rode those swells, yet the long average has stayed low enough, for long enough, to let complexity slowly gather. We did more than survive beneath it. We were composed under it, calibrated to it, made of a chemistry that only holds together because the dose has stayed this gentle for billions of years. It has the shape of a candle that stays lit only because a hand is cupped around it against a wind. The flame does not feel the hand. It does not see the wind it is being spared. It simply goes on burning, steady and upright, in what seems to it like perfectly still air, never knowing that without the hand it would have guttered out long ago. We are the flame. The still air we have always taken for granted is a wind held off by a shelter we have only just learned was there. Bring it all the way down to where you are. Inside you, at this very moment, in cell after cell, that ancient repair machinery is at work, reading your genes, finding the small breaks, mending them, keeping the long instructions of your body legible against a trickle of damage that never quite stops. It is winning, easily, comfortably, because the dose it faces is the gentle one a sheltered world allows. The calm in your cells tonight, the quiet success of all that mending, is the innermost echo of a bubble 11 billion miles wide, holding back a flood you will never see. We have lived our whole existence inside that shelter, every one of us, never once stepping beyond it. Almost nothing we have ever made has stepped beyond it either. In all of history, only a handful of objects have ever carried enough speed to leave the sun's protection for good and never return, and Voyager is among the very first of them. What does it take to truly leave? We have launched a great many things. Thousands of spacecraft, across more than half a century, satellites and telescopes and landers and probes scattered through the solar system. Nearly all of them are still bound to it, circling the Earth, orbiting the Sun, looping around other planets, held by the same gravity that holds us. Out of everything we have ever sent up, only 5 objects have gathered enough speed to leave the solar system for good and never return. What sets those 5 apart is not the distance they have covered, but the speed they carry. A spacecraft can travel enormous distances and still be a prisoner of the sun, climbing out and falling back, or settling into a long captive orbit. The craft that spent years circling Jupiter or Saturn went vast distances and saw whole worlds up close. Yet every one of them remains the sun's prisoner, and always will. Escape is a matter not of going far enough, but of going fast enough, of carrying more energy than the sun's gravity can ever claw back. Below that threshold, the sun always reels you in eventually. Above it, you are free. And these 5 are the only human-made things that have crossed the line from bound to free. There is only one way we have ever found to reach that speed. To break clear of the sun outright from where the Earth orbits would take something near 40 kilometers a second, far beyond what any rocket delivers on its own. The extra energy has to be borrowed, stolen from the motion of a giant planet in a close, precise pass, the kind of slingshot that flung Voyager onward at Jupiter and again at Saturn. Every one of the 5 did the same. Each used the gravity of a giant planet, Jupiter above all, the only bodies massive enough and swift enough to hand a small craft the speed it needed to break loose. Without a giant planet to push off, there is no escape at all. It has the shape of a field of seeds in a wind. Most of the seeds a plant lets go simply fall back into the same field, settling near where they began, bound to the ground that made them. Only a rare few catch a wind strong enough, blowing at just the right moment, to carry them clear over the last hedge and out into the open country beyond the field entirely. The giant planets are that wind, and the rare alignments that let a probe reach them are gusts that come, at most, once in a generation. 5 seeds, in all our history, have cleared the hedge. They make a small and strange company. 2 of them, the pioneers that went first, fell silent decades ago and drift on now without a word. One of them aimed at a star it will not pass for 2 million years. One, the youngest, is still crossing the outer solar system and has not yet reached the edge, with years of travel ahead before it even meets the boundary the Voyagers crossed. And 2 are the Voyagers themselves, the only ones of the 5 that have passed beyond the heliopause and are still, for a little while longer, sending word. Of everything humanity has ever made, these are the only objects that have both left the sun's shelter and lived to report from the far side of it. There is a quiet line being crossed in all of this, larger than any single mission. For the whole of our existence, everything we are and everything we have built stayed inside the sun's domain, one family of objects belonging to a single star. These 5 are the first to step out of that family and into the galaxy at large, the opening handful of human things that will spend the rest of time not as part of the solar system but as part of the Milky Way. And the company is in no hurry to grow, since no mission now flying was built to follow them out, so for a long time these 5 may remain the whole of it. A small number to mark so vast a threshold, beginning the long human residency among the stars. Reaching that speed and crossing that line was never the hard part by itself, though. The hard part was building something that could survive the journey, decade upon decade, failure after failure, far beyond any reach of repair. Voyager has broken, more than once, alone in the dark. What did its breaking teach us about how to make a thing that lasts? Voyager has failed, more than once, in ways that should have ended it. Its sense of its own orientation went haywire. A patch of memory corrupted and turned its words to nonsense for 5 months. And each time, against the odds, it was brought back. How a 47-year-old machine survives failures like that, 14 billion miles past any hope of a repair crew, turns out to be a quiet manual for building a thing that lasts. The most telling of those rescues was the most recent. When that patch of memory failed, the broken part could not be fixed. It was simply dead, unreachable across the gap. What saved the spacecraft was that its makers had built it able to change itself. The team could command it to lift the lost code out, break it into pieces, and tuck those pieces into other corners of memory that still worked, rewriting the machine's own layout from 11 billion miles away. No one in the 1970s knew that exact failure was coming. They could not have. What they did was build in the freedom to rearrange, the room to route around damage they could not foresee. The first rule of making a thing that lasts is to make it able to become a slightly different thing when part of it dies. Then there is the older and plainer choice to build everything twice. Nearly everything that mattered on Voyager exists in duplicate, so the failure of one piece can be answered by its twin, and the whole craft was designed to lose function gracefully, a little at a time, rather than all at once. It depends not on every part working, but only on enough of them working, and on being able to set aside the parts that fail. A thing built to last is built not to be perfect, but to keep going while imperfect, shedding broken pieces without collapsing. Voyager also survives because it is, by every modern measure, almost laughably simple. Its computers holding mere kilobytes, its systems plain and unclever, with nothing delicate to break. Everywhere, its makers left margin, building it to withstand far more than the mission asked, which is why its instruments kept working in a cold tens of degrees below anything they were tested for, and why it came through the savage radiation around Jupiter intact. More advanced would not have meant more durable. The dense, intricate electronics we build today, for all their power, are fragile, and few of them would still be speaking after half a century in deep space. Simplicity and slack, not sophistication, are what carry a thing across the decades. It has the shape of an old stone bridge still standing after centuries, while newer, cleverer ones have come and gone. The old bridge survives not because it was advanced, but because it was overbuilt and plain, heavy with margin, carrying nothing fine-tuned that time could find and break. It was raised by people who would never cross it in their old age, built to outlast them, and it has. Voyager is that bridge, thrown not over a river but across the decades, plain and overbuilt, and still carrying its small traffic of signals home. There is one failure none of this can answer, of course. Redundancy and margin and clever rerouting can carry a machine through nearly anything except the slow loss of its own power, the one breakdown no spare part or rewritten line of code can route around. Even the best-built thing meets a limit it cannot design away. And the hardest part of all was never the hardware. What nearly ended Voyager was not only a broken chip, but the risk that no one would still know how to fix it. Every rescue leaned on people who could read an obsolete language, followed decades-old manuals, and in the worst moments on retired engineers, called back to decipher code they had written when they were young. To build a thing to last the deep future means keeping alive the knowledge of how to tend it, handing that knowledge down a chain of people long after the makers are gone. The object can be built to endure. The understanding has to be carried. We are forever building things meant to outlast us. Archives and monuments, the long burial of dangerous waste, messages we hope someone will still read in 10,000 years. Voyager is a small, working example of how that is actually done, not through cleverness but through humility, through redundancy and margin and plainness, and through the patient handing down of how a thing works to people the builders will never meet. To build for the deep future is to design for your own absence, and to trust strangers to carry it on. Most of what we own is built to be replaced, to fail just past its warranty and be thrown away. Voyager was made the other way, careful enough to forgive its own aging, to break a little and keep going, to be tended rather than discarded. It is good to be reminded that we still know how to make things like that when we decide they matter enough. The care that built it and the failures that tested it are only half of what Voyager leaves us, though. The other half is what it found, and that reaches further than this one craft or this one sun. What the edge of our own bubble turned out to be tells us something about the edge of every other stars. Are there bubbles like ours around the other suns? For most of this story, the heliosphere has seemed like our particular possession, the sun's own bubble, the edge of our own world. It is nothing of the kind. Every star that blows a wind blows a bubble like it, carving its own cavity into the gas between the stars, holding its own boundary against the galaxy. The galaxy holds hundreds of billions of stars, and nearly every one that breathes a wind makes such a bubble, so the Milky Way is filled with these cavities, uncounted billions of sheltered pockets scattered through it. Astronomers have a plain name for the other bubbles. They call them astrospheres, the same structure the sun makes around other suns. And some of them we can see. A star moving briskly through a dense patch of interstellar gas plows up a glowing arc ahead of itself, a bow wave lit in the infrared, the visible signature of its bubble pressing into the medium, and telescopes have caught these arcs around star after star. We can even sense the boundaries of some of them directly. Around other stars, the same pileup of neutral hydrogen that gathers at our own edge collects into what is called a hydrogen wall, and it leaves a faint fingerprint in the star's light that our instruments can read, the distant cousin of the very pileup Voyager, measured by hand. What Voyager crossed at our own edge, other stars wear as a faint, shining curve, seen from the outside, light years away. Every astrosphere but one, though, we can study only from the outside, as a distant glow or a shape against the dark. The heliosphere is the single exception, the one bubble in the universe we can measure from within, with an instrument actually inside the wall, Everything Voyager learned the hard way. The pileup of gas at the boundary, the trading of atoms across the seam, the field combed into alignment, the pressure 10 times what we expected. All of it is the only ground truth we will ever have for what the inside of such a bubble is truly like. When we look at a glowing arc around a distant star now, we read it through what Voyager felt out at our own edge. The one example we live in teaches us how to interpret every far-off one. And because Voyager broke so many of our predictions, the lessons run deeper than mere confirmation. The missing physics, those surprises exposed, the hidden particles, the swapping of charge, the draped field, the magnetic pressure, were never quirks of our sun alone. They are general processes, at work around every astrosphere in the galaxy, ingredients we never knew to put into the models until one spacecraft, at one boundary, forced them in. Voyager did more than map our own edge. It corrected our understanding of every edge, like ours, everywhere. This reaches all the way to the question of who else the galaxy might shelter. If the protective bubble is not a special gift to us, but a generic thing any star with a wind makes, then the shelter that helped make complex life possible here is available, in principle, around countless other stars. The precondition we found written into our own existence may be written quietly all across the galaxy. The shelter is far from equal everywhere, though. A bubble's size and strength depend on the star's wind and on the gas it travels through. So a star with a feeble wind, or one crossing a dense cloud, may hold only a small, squeezed bubble that shields its worlds poorly. The most common stars in the galaxy, the small red dwarfs, often have weak winds and violent tempers, and the shelters they offer their planets may be thin and unreliable. Every star has an edge. Not every edge protects what lies within it, as well as ours has protected us. It is the experience of knowing your own harbor so well, every shoal and current and depth of it, from a lifetime spent inside, that you can look at the bare outline of a coast you have never visited and read its harbors at a glance. You recognize the shape, the way the land must curl to make safe water, the places a boat could shelter. Voyager gave us that close knowledge of the one harbor we live in, and with it we have begun to read the coastlines of stars we will never reach, recognizing in their distant outlines the same kind of sheltered water we were born in. There is a particular turn of feeling in learning this. For most of the journey, our bubble felt singular, the edge of the only world there is. What Voyager's findings hand back is something stranger and larger, the knowledge that ours is one bubble among uncounted others, that the strangeness at our edge is the ordinary strangeness of every star's edge, and that whatever made us possible here was never a private miracle, but a common condition of the galaxy. It makes us less singular and more connected, one sheltered harbor among a sea of them, the only one we happen to be able to measure from inside. And that may be the quietest thing Voyager leaves behind. Not a single discovery, but a way of seeing, a piece of understanding that will outlast the spacecraft and its makers and keep being true long after the last signal is gone. A machine that will fall silent within years has handed us something that does not fall silent. What is it, exactly, that a thing like this leaves to those who come after? We tend to picture a legacy as something finished. A monument raised and left standing, a work completed and set down, an achievement we look back on, fixed and done. What Voyager leaves behind is not a finished thing, but a source that has spent 47 years correcting us, and whose corrections do not stop working when the signal does. For nearly 5 decades, it has handed back one finding after another that overturned what we were sure of, and each was a correction, a place where reality outranked the diagram and we had to redraw. That is a stranger inheritance than a monument. A monument asks nothing of you. It sits, complete, and you admire it. A correction keeps working in your mind long after you receive it, quietly reshaping how you see everything around it. Voyager left us not a thing to look at, but a changed picture of the universe. And a changed picture goes on changing what you see through it, with no end. Those corrections are woven now into the textbooks and the models, into how everyone who studies these questions is taught to think, carried by people who were not yet born when the data first came down. In a real sense, it is still reporting, even now, even from data long grown old. The faint, continuous hum of interstellar space was never heard in the moment it arrived. It was found years later, buried in recordings no one had fully read. Findings are still being drawn out of data Voyager sent home decades ago, and they will keep coming for years after the spacecraft itself falls quiet, the way a letter can be read and reread and yield something new each time. The signal will end. The reporting will not for a long while yet. There is an irony folded into this. We bolted a careful, polished portrait of ourselves to the side of the spacecraft and sent it outward, a curated message meant to announce who we are. But the message that has mattered most is the one that came back, and it was nothing curated. It was raw, surprising, often unwelcome truth about a universe that refused to match our expectations. The legacy of Voyager was never really the story we told the dark about ourselves, but the harder, truer story the dark told back. And this inheritance is not the kind you simply receive and keep. Voyager left us its answers, and it left us its unanswered questions too, the true density it never reached, the real heading of the field it did not live to measure, the energy still unaccounted for. Those open questions are part of what it hands down, and they do not sit quietly. They ask something of whoever comes next, to build the next instrument, to send the next traveler, to carry the looking forward. Already there are designs for a probe meant to follow Voyager out and reach the true interstellar medium it never lived to measure, a successor shaped in part by the very questions Voyager left open. The task has already been taken up. It has the shape of a teacher whose corrections keep arriving in your mind long after the teacher is gone. The voice falls silent, the person leaves, and yet years on you catch yourself thinking more carefully because of something they once set straight, hearing the correction still, working in you, shaping what you notice. Voyager is that teacher now, near the end of its speaking, having already lodged in us a way of seeing the edge of things that will go on correcting our errors long after the last word has faded. Not a closed account, finished and filed away, but a living one, a thing that still asks, still teaches, still has more to give from what it already gave. We were handed, by a machine and the people who made it, not a final answer, but a better way of asking, and a few hard questions held open for us to carry. That is more than most of what we build ever leaves behind. For all of that, though, this whole journey has played out at a distance we can barely hold in the mind, 11 billion miles and more, in a dark almost beyond picturing. And the strangest thing left to say is that none of it is truly far away. Every law Voyager met out there at the edge is at work, this very moment, in the room where you are lying. Where does all of it finally come to rest? All of this has happened very far away. The edge 11 billion miles off, the bubble 1,000 light-years across, the probe drifting somewhere past 14 billion miles in a dark almost beyond imagining. It is easy to feel that the whole story belongs out there, in places no body could ever go. It does not. Every law we followed to the edge of the solar system is at work right now, in the room where you are lying. The same flood of high-energy particles that Voyager measured beyond the boundary is falling on you at this very moment, thinned to a soft and harmless sleet by the same shelter we traced all the way out. A few of those particles are passing through you as you breathe, the faint survivors of stars that died long before the sun was born. And in cell after cell, quietly, the small machinery that mends what they break is doing its patient work, winning easily, because the dose is gentle, because the bubble 11 billion miles away is holding back the rest. The calm in your body tonight is the innermost edge of that shelter. The physics does not change between there and here. The same force that combed the galaxy's magnetic field into line at the heliopause is the force that holds every atom of you together. The same moving charges that ring the interstellar plasma into its faint, steady note are the moving charges that carry every thought across your nerves and every beat of your heart, the slow electrical tide of a body at rest. Even the iron in your blood, the iron that takes up the oxygen in every breath, was forged in dying stars, the same kind of stellar deaths that blew the hollow we shelter in. The shelter and the body inside it were built from the same fire. You are not watching this universe from outside it, but made of the same handful of laws we followed to the edge, running here in the warm dark at the scale of a single quiet life. And Voyager is still out there, this very moment, as you lie here. Right now, tonight, it is more than 14 billion miles away, coasting outward at close to 1 million miles a day, exactly as it has through all these hours of listening. Its small nuclear heart is still warm. Its faint voice may still be reaching us, a whisper thinner than 1/1000,000th of a watt, caught by a great dish somewhere on the turning earth. While you have lain here in the quiet, it has traveled another 100,000 miles or so farther into the dark, and it has not stopped, and it will not stop. There is an unbroken line running between the two of you. From the boundary 11 billion miles out, through the sheltered emptiness, down past the planets, through the air of the room, to the breath rising and falling in your chest, the same laws hold the whole way without a single break. The edge of the solar system and the warmth of your own body are not two different worlds, but two ends of one continuous thing, ruled by one continuous set of laws, and you have been resting inside it this entire time. Perhaps that is the quiet thing to carry down into sleep. Not how far away the edge is, but how near. The vast, strange boundary that broke every prediction, the bubble blown open by dying stars, the lonely traveler crossing into the deep, all of it is bound to you by the same physics that is, right now, keeping you safe and warm and breathing in the dark. There is nothing out there that is not also, in some quiet form, in here. So when the last signal from Voyager finally fades and the great dish hears only the soft static of the universe, the thing it spent its life learning will not be lost. It will be here, in the calm of a sheltered world, in the steady mending inside a sleeping body, in the plain fact that the edge of everything and the quiet of this moment are cut from one unbroken piece. You came out here, late and quiet, to understand something true, and you did. Thank you for staying with it, all the way to the edge and back. The same calm you feel in this dark room reaches, unbroken, out to the edge of the sun's long shelter and a little beyond it, where something we made is still traveling on through the night. Rest easy. The bubble is holding. Good night.